Okay, so we are live right now. Before speaking the rest in English, please let me allow to speak some words in Spanish. Así que vamos a dar la bienvenida a todo el mundo a esta gran aventura espacial que es precisamente las edades de Marte. Curso de verano para el cual estamos encantados de poder estar aquí. Es muchísima gente a la que le tenemos que dar las gracias. Voy a empezar ahora precisamente a darlas en español. Y bueno, obviamente pues empezamos por el Ayuntamiento de San Lorenzo del Escorial, que nos ha facilitado un montón de material y espacio para poder hacer esto. Y por supuesto el Hotel Los Lanceros, que es donde lo estamos realizando. Y también muchísimas gracias, como no podía ser de otra manera, y luego lo voy a repetir en inglés, pues por un lado a David Pacios Izquierdo y a Sara Ignacio Cerrato, que digamos son los responsables de toda esta maravilla tecnológica. Particular de lo que es el Ayuntamiento de San Lorenzo del Escorial, no me quería olvidar de la Concejalía de Cultura, con don Enrique París, que es precisamente el concejal, y por supuesto para el aspecto técnico, pues Javier Montenegro, y para el aspecto de prensa, pues a Virginia, que nos ha facilitado mucho. And now, please let me return to English. So, many thank you for being here to this great adventure of flying to Mars in just 1 week. Just to review in 1 week what has been done before. I wanted to start this summer school with a famous phrase, which is Mars, the final frontier. So these are the troubles of some people from a European project that you will know in the upcoming days, which is about building and designing and building an instrument for the Martian surface. But of course, this summer school, which is part of one of the work packages and deliverables of this European project, puts together many people that have been working with us in the past, and we are continuing to work with them, and even we have some future collaborations ongoing. So this particular project is co-founded by the Horizon 2020 program from the European Union. We have our coordinator here, which is Alessio Deuterium, and he will give you not one but 2 talks during this week. But let me just show you what is going to be our journey during this week. So this first day is the day that we are going to lift off to planet Mars. And it's impossible to lift off to planet Mars without the help of the different space agencies that are around the world. So we'll have many, not only important, but very interesting people speaking today and some of them speaking tomorrow that pertain to these space agencies that allows us to have these incredible environments to research, to teach, especially to pass the leverage to the next generations that are accompanying us here. Tomorrow, if we're going to travel to planet Mars, we need to learn some basics of planet Mars, especially that we cannot breathe right now on planet Mars. Aspects like geology and astronomy. Then Wednesday is going to be devoted to a particular implementation of a European project that has to do with planet Mars. And this project is actually INTIME. And we'll start with a talk from Alessio Deuterium, and then we have several partners that will discuss different basic aspects of Martian science that has been taken into account for this project. And Thursday is going to be devoted to engineering. Okay, we have the basics of exploring planet Mars, but then we have to design the new bleeding edge instruments to explore planet Mars, and even to learn more about it. Because our knowledge of planet Mars is still not 0%, but I mean, there is much to learn. And finally, we cannot leave our references, our popular culture references. We're going to talk about not science fiction, but actually science fiction that has lost the fiction word. And we're going to talk about Mars colonization and what is being done right now for colonizing Mars from the different works that are being done from our research groups. So actually what we are, just a little spoiler, we're going to talk about growing crops using Martian soil and what we are doing right now about that. Let me remind the people that are connecting right now to YouTube that we will pass all your questions to our speakers. And if you're doing in Spanish, we will also do the translation to them. So thank you very much for attending this very first session to be so early. I'm going to leave the floor to the next speaker, who is going to be Luis Vázquez Martínez.
Okay. My presentation is in Spanish, but I will talk in English. So in this way, it's a simultaneous translation, really. I'm going. Everybody that like to have a copy of my presentation, ask to the direction, and we can send the PDF. So it's not a problem. So I'm going to summarize certain aspects of this meeting, in the sense that it's a consequence of the existence of a Martian group in Complutense University. Also, the Polytechnical is involved, but really we cannot understand these actions if there is no a big group. Actually, when we started with the Martian creation in the Complutense, I will say publicly one main thing. The people that we were involved before, we did not have a space experience. But the important issue is that the physical laws, mathematical laws, and chemical laws are the same in the Earth and in Mars. So for this reason, the people who was expert in atmospheres in the Earth, was involved in geology and so on. So actually, the Complutense, the nice thing, is a big university with studies in different areas. So we were able, by a kind of astrological coincidence, to involve people to study that. So it is the context of that. So, is this, es esta, no? Este. Okay. Okay, so actually we already organize summer courses, but this year, as Professor José Luis explained, it was a special one. But always that there are difficulties, there is the possibility to develop the imagination and to solve variational problems with constraints. We have to thank this collaboration with a group of ALMA in Italy, of Alessio, that he already is an expert in many space adventures. And so we were involved, and this is why we are able to organize this meeting here. So I'm going to say some summarizing. This is our symbol in the Complutense, the UCM Martian Studies Group, As you can see, they are the two satellites of Mars, Phobos and Deimos, and the universal colors indicated for Mars are these. Really, I don't know as to very well the origin, but it appears in the literature that this is the colors of the planet Mars. So we are going to summarize something. Actually, to tell some historical event, that in Spain it was already interest for Mars in the 50s. I suppose many of you still were not in project. So it was in the 50s that we have the Observatory of Madrid. They were studying some effect with the telescope that now you can enjoy there. And there is a movie, a video in the Nodo. The Nodo for the Italians is the Luce. So it's the equivalent to Luce. And you can see this video in the 50s. They were explaining about the possible origin of life in Mars. It was very naive. I was very happy to find this video because the authors, this professor, they were my professor after in the Faculty of Physics in the Complutense. So it really, after we came to the in the geological faculty already was created, and after the push to create this atmosphere, it was the creation of the Center of Astrobiology associated to NASA in INTA. Actually, it was also an astrological coincidence of many people from Complutense, Autonoma, Polytechnical, that we coincide to organize that under the Professor Eret Mercader. So, actually, sorry. So, it is the context of the exploration of Mars is a driving force that the people always try to find answer to where we are going, are our coordinates in the world. So, and the idea is to try to find out if there is life abroad. As you know, 500 years ago, it was checked that the Earth was not the center of the universe, but now the open question is to see a life, because until this moment we know in the Earth, but what happens with the other? So, actually, it's true that any step in space generates illusion, generate new scenarios of innovation from the science and technological point of view. Historically, you have from the first Sputnik, Gagarin in the first flight. So it is always, even there are many problems on the Earth, but these goals are very important for to become enthusiasm and generate new scenarios. So one thing is to see what is the life. A life is very difficult to define, but we can say things about what is life. I think the situation with the life definition is like in the Rinascimento in the University of Salamanca. Somebody asked to a professor, what is the space and time? And he said, I don't know what they are, but I can speak about them for many years. So it is what is life. We know aspects of life, but still is not quantitative, and we cannot say. And this is, we are lucky that we don't know exactly what is life, because that means that there is a lot of work for the next generations, because you can imagine that everything is set up, so it's to no possibility to work. So, so in the Mars, as you know, the first observation of Mars were made by Galileo in 1609. I mean, in Firenze you have a copy, of the same telescope. And I will say how these scientific issues introduce innovation and technological effects. As you know, if you are going to Venice, now is difficult because you have to book in advance to go because there is a lot of people. That there is a tower and there is a place there indicating of Galileo. And why? Because the Doge of Venezia was the first one to buy a telescope, because in this way he was sit down in this tower near the cathedral and could see the boats and the stocks they bring. So they knew he knew in advance to negotiate with the product arriving to the dock. So it really is a simple case, but historically, if you are going to Venice, I advise to sit down, and it is the indication. So comparing with Mars and the Earth, you know, the gravity is 1/3 of the Earth. The Martian day is almost the same. But the Martian year is twice, because that means that Mars needs twice than the Earth to around the Sun. So this is why I will say personally I use this effect when they ask me my age. I always say, please, if you know physics, you must ask in which system of reference you ask me the age, because in the Earth I 72, but in Mars I 36. So really, it's a good aspect of this tangential. So, is the composition of the atmosphere is mainly CO2. Is simpler than in the Earth. So because and you have some dynamics. So the pressure in the surface is like here in the Earth at 40 kilometers in the air, and the difference of temperatures is very large, 15 degrees. Around in 1 meter of difference. As you see in Mars, the fluctuation of temperature are not smooth like in the Earth because they have no ocean. So in this way is the surface, I'm not going in details. As you know, the main landing missions is in the upper part of the Earth because the regularity of the surface, is nothing more than that. So the questions is the existence of water in the past and in the present. Actually, there are many elements that show the past existence, but one scientific proof was when they found jarosite. Jarosite is a rock that was found in the 19th century in Spain, in Almeria, in El Jaroso. And we know from chemistry that to have jarosite, you need to have water in a certain step. So if we find jarosite, means that in a certain step of the formation, we had water. Apart of the landscapes and other issues, the magnetism, as you know, in the Earth we have a magnetic field covering the whole planet, but not in Mars. We have, in a certain way, certain areas of magnetic field. And it's curious that they are able to generate auroras, not like the the wonderful auroras that we can enjoy in Lapland during the meetings of Professor Arimati in Ivalo that you observe. This is now a good area to work, because in the missions you have several instruments, and the idea is to cross the data from different instruments to detect the auroras. The auroras is nothing more than the radiation emitted by charged particles that are trapped by the local magnetic fields. But we don't have a protection with that. This is due to the dust, atmospheric dust. You can see this picture that I remember is from 23 April, and the Spanish know what means 23 April is related to Miguel de Cervantes, I think. So is the color. So in the earth is blue, but in Mars is red. So it's the opposite that. Actually, I saw recently a science fiction novel that is speaking about some events in the periodicals. I mean, actually, there is not a quiet surface. There are many things, and you can see here some. This is comparing a picture 1999 and 2005, and you can see a new deposit there. So it seems that now we are in conditions to compare in periods to see how evolved and how is the activity. That means that this is internal activity. It's not clear. Now with the mission inside, they detect some earthquakes. But anyway, if the geologists are more expert in this issue, but it's a question that to see. So, and this is the other one obtained with the Mars Express, with the chamber. It was amazing to see how it was changing the shape. And this is a picture, a family picture of the rovers. The famous one, the Sojourner, were the first one to move. The first one, sorry, I moved to this. Okay, so it was the first one to move. After came a spirit and opportunity, and after curiosity. So as you can see, the size is, in this case, we can say that the size is related to the intelligence of the robot. So they are more intelligent. So this is the payload of that. It was the CAB, the Centro de Astrobiology, was involved. I was in the beginning the PI. It was an amazing period because we start to learn many things. And for me, that I coming from science was the opportunity to be involved with the engineering. So it was the letter sent to CAB, and this is the distinction. Okay, but anyway, I come into the mission that really gave a push also in the Complutense was the MedNet mission with with Finland. Actually, the driving force for us was Finland. I must thank publicly that we start to learn many things, and it was in collaboration with Russia, and even did not fly up to now, but many of the instruments developed in this mission are used. So really, we create in INTA was the main supported, but also the universities, an environment of the questions to generate international relations and so on. It was the flux of this moment. I hope that this difficult period will finish and we will arrive again to an asymptotic state of peaceful period, but anyway, it is a hope. And I mean, to say the instruments that were built in INTA about the radiation, and this is I mean, is a set of stations that to create a network of meteorological stations. So it is, I mean, I'm not going into details. If, as I told in the beginning, if you like to have a copy of the PDF, you can have it, it's not a problem. So, and one thing that allows us, it was that at that time we start with a group of cloud computing in the Complutense, and we developed some results that after we apply in the collaboration with NASA. So now at this moment, actually we are in a year, in a period in which new knowledge will appear. I think it's a period that stops now and start with the three missions. The NASA Perseverance, the mission Hope of Emirates, and the Chinese one. Unfortunately, for the moment, the European mission with Russia is stopped, but anyway, I hope it's frozen, and when the ice will disappear, maybe, because what is important is that the knowledge is there and the achievements are there. So can be in this sense. So it is the Perseverance. I mean, they have the helicopter. I mean, it's more complicated than Curiosity, as you can see. And this is the Emirates. The Emirates, they have only, they don't have a rover. They have an orbiter. And up to now, they are working very well. And we have a strong collaboration now between Complutense and Emirates. And unfortunately, by bureaucratic reasons, the representative is not able to come, but is going to come through the 2 dimensions of the telecom. So unfortunately, so is to cross the databases. Actually, here, I mean, is the thesis of David, is the driving force with his thesis of this collaboration, and they are crossing about 500 data with another basis of 300. Actually, is to cross, so it really, in this sense, hope, I mean, is the characteristic of the missions, and this is, and the Chinese, as you can see by the letters at the beginning, is the Chinese mission, is that is with rover. So is the mission, and they have, I mean, they are still different instruments. I mean, is got, but the nice thing, and for the future, actually in our group in Complutense, we have the projects with addressed by Dr. Alessio Diorio. That is the project INTIME. We are collaborating with the Auroras for the issue with ESA. The other is the project A. I mean, still, the nice thing in Complutense is that now we create a network of relations and collaborations that are the driving force for the young people that coming to do the thesis. And this is the collaboration with the IKI, with the Russian agency. I will say also, it was mentioned before, the INTIME is to construct an instrument to date the rocks. I mean, it's mainly a huge work of the geologists from the project. Actually, I mean, it is based in luminescence. I mean, I'm not going to in detail, but anyway. And this is another issue is to cross the data basis of the Marses and SPCAN to detect the auroras in Mars. Actually, it's one of the first time that we cross the data of two instruments in the same mission, and they observe events that are related each other. So actually, you can have here is SPCAN is a spectrometer atmosphere of ultraviolet, and Marses is the Mars Advanced Radar. So actually, it is the question, of course, the data are obtained in each instrument, but we have to define a dictionary to compare each other. So it's not, it's a hard work, but the nice thing of that is that we are developing certain scenarios that can be applied to another problems. So because it's data. Actually, as you know, I don't know in other countries, but in Spain now, if you apply for a project and there are not two classic words, a climatic change and big data, you are the anti-set. So actually, it's important to have in mind that. So it is already developed. The initial attempt to because how you take the data, I mean, and the first aurora was discovered was in 2005. So and now we are trying to detect in the data the crossing. Age is another project which is amazing, that is to apply the set of pictures obtained from satellites to see the evolution of COVID. And why? Because you can see, for instance, here this picture that appeared at the beginning of the COVID. If you compare the atmosphere in China before the COVID and after, the pollution, it was not controlled. And so with this idea, we compare the containers in the airports, and I mean, and you have here actually after the Galileo coming again a picture of Venice that you can compare the traffic in the dock of Venice before the pandemic and in the pandemic. So by comparing this, I mean, the people involved in the project are able to obtain some economical models about the flow of market. I mean, it's very fantastic. So the project, I mean, and we are participating, Complutense, Tor Vergata, I mean, in Poland, Greece. So it is the nice thing of this European project that is crossing people from many areas and many countries. So in this way, it's very stimulating for the young people to travel and to do it. And finally, I will say about the collaboration we have. Somebody will say, but it's possible now in the present situation. It's difficult, but as you know, the reality is in any dimension, not in 2 or 3. And we have still, the collaboration is the following, is to see new materials, because one issue is that for the next generation of space travel, you need materials that can absorb the radiation or can become invisible. Because you can imagine a 5 months of travel to Mars, you have to be protected from the radiation, electromagnetic, and particles. So it is collaboration with the Polytechnical University in Madrid, Complutense, and also the Russian Academy of Science. So it's very simple idea, so I'm not going, is this one. As you see, the Maxwell equations are the equations that control the evolution of electromagnetic fields, and in this equation appear two parameters characterizing the media, epsilon and mu, the permeability and electric. But for the natural materials, epsilon and mu are positive. But what happens when epsilon and mu can be either positive or negative? Actually, the first one who introduced this concept was Professor Veselago from the Russian space of IKI. It was at the time related, and he was very, nobody could understand that. But the nice thing that he introduced, not creating a special material, because there is other technique, creating a special arrangements of geometries to find materials with epsilon and mu. Actually, from the mathematical point of view, computational and physical is very open field, because you can find many aspects. And this aspect is also related to the following fact. How you analyze the structure of an object. You send an electromagnetic wave to the surface, and you evaluate the reflected and the scattering data. This is the radar foundation. As you know, now there is a lot of work in trying to find the quantum radar. It is another philosophy of that, but are working, as far as I know, in Canada and Russia. Because the problem is that the classical radar cannot work very well when you have a strong turbulence, magnetic, atmospheric, like in the North Pole. So in a certain way is the quantum radar, and are progressing very. Actually, I saw recently a conference how to detect with the quantum entanglement. I mean, as you know, a concept which appears there is the quantum entanglement, to detect if there is life in a star. The star is maybe far away, is 2 years light, but you can have two photons entangled, and you send one to the star, and because they connect each other, you can extract information. I think really this situation, it looks science fiction, but it looks like at the beginning of the last century, some people say that never we could analyze the materials of a star. But when the spectroscopy came, after that, you can analyze and evaluate the radiation, from the radiation, the nature of the atoms that emit this radiation. So, and one issue is that if you compare the wavelength and the dimension of the properties of the medium, so depending on this ratio, you have the behaviors are very different. To be a summary explanation of that, because I suppose many of you are going to a beach or close to a river. If you are going to a place which is smooth, so you are able to walk in a peaceful way, because the wavelength is the equivalent to the dimension of your feet, but the properties of the medium are not changed very fast, are changing very smooth. So this is like, but when you have many stones with the dimensions less than the length of your feet, you cannot walk. In this case, we will say that we are in the anti-aconal, so the properties of the media are changing very fast compared with that. So actually it is a key point, and actually here we have some joint publications. Actually the last one we published in the last year, but the important issue in this case is not creating new material, but new configuration of dielectrics. The dielectric, as you know, physics is a very special material, not well studied, and with that is obtained that. So it is the properties, and we arrived to a conclusion in these experiments that for certain frequency the material is invisible. So actually the invisibility, as you know, is a mythological concept introduced by Plato in the book number 2, in which the ring of Giges, he was in Greece, and he found this ring, and he saw special properties that become invisible, not invisible. So really, Plato is doing an analysis in terms of laws, but is related to talking in the Lord of the Rings. Yes, really. Actually, as far as I remember, in this film they don't talk about Plato, but really the idea is there. Of course, after you have the Harry Potter, who, as I know, Harry Potter, so that means that with the new materials you can implement some philosophical and ideas that look a dream. You can imagine to sell invisible dress in the door of the parliament. It will be very good because everybody will change every day of the dress and will be invisible. So I mean the application of that is amazing, and the possibilities, and for the young people that are very related to the video games, I think it's a good laboratory. So this is Harry Potter, Titanfall, and this is the agreement we have, I mentioned before, with the Abu Dhabi, with the, is the problem that by bureaucratic reasons, I will say, Dumitru will talk in 2 dimensions, but not in 3. And even Jose Luis organized the trip 5 months ago, but it was this amazing bureaucratic steps that, because as you know, the university in Abu Dhabi is very special. It's a set of campus of American American universities. There is Harvard, Princeton, New York. So our contact was with the agency through New York University. Is the possibility, and now become some problems of the visa. As you know, when you try to stop one issue, you find infinite ways. Actually, the university was able to call, but anyway, I hope that anyway in this year they will come at a legation here. So it is the agreement. This is the book that is a summary of our activity. Actually, we published the last year in the pandemic, and we are going to have a small event today of official presentation of the book, in the sense that summarize our activity in the Complutense and the people. So, and this is to thank you very much for the attention. Okay. Any questions? I will be very glad. Actually, as you know, the nice thing of space is that it has no boundaries. It's interdisciplinary, multidisciplinary, and no fraud. And now the nice thing of Mars is that there is no COVID there, is for the moment. Okay.
As far as we know.
Yes.
So, any questions from the room? ¿Alguna pregunta en español?
Okay, so because it's not going to be finished, the exploration of Mars this year, even it's important to know that with these 3 new missions, we'll start a new period of new knowledge. Okay. Ale.
And, Luis, please.
But Luis, thanks for your very interesting talk. But how would you imagine making use of those invisible materials in Martian investigations?
No, the invisible means that, if you, I start to understand this issue by reading this small book about the physics of Star Trek, in which they say that, for instance, in the movie 2000, Odyssey in the Space, some noises there are not true. You can hear only 2 noises, the breathing and the heart beating, but not the explosion outside the mission. So invisible means in this context, as far in the cases that were obtained with this, that you send microwaves. Actually, at this moment, they are mainly with the microwaves and the other. So you are not reflecting nothing. If you don't reflect, you don't see nothing.
I just wanted to appreciate, Luis, the wide spectrum of your research, ranging from, let's say, basic mathematical problems into practical Martian research. So thank you, Luis, very much indeed.
Okay. No, actually, it's, in my opinion, the invisibility is a driving force for many studies, because it's not well understood. But it is, for instance, also, there is a line of research in this direction to find the magnetic field creating the radiation impacting in the electrics, because the idea is to create a magnetic field around the orbiter and to protect from the radiation of particles with mass, because it's not only the electromagnetic but also other one. So it's a problem, of course. I arrived to say that some in the ESA, some group, I don't know, in the medicine or something like that, they were testing some products to see how they absorb the radiation, in the sense that it's a way to protect the astronaut. But it's a field that very open there. Actually, this is other indication that maybe can be treated in the next meeting you're organizing in Lapland. Okay, so it is okay. Thank you. Thank you.
So we will give something like 10 minutes break, as we are now trying to connect with the next speaker, who is Dr. Oleg Koroblev from IKI, Russia. So you understand that there is some tricky aspects. So thank you very much for attending this first part of the first session, and see you in 10 minutes. Thank you.
Sorry, I cannot. What? My phone is something. Well, I am very glad to be with you and to present some results out of our selection of results from our experiment on PGO. So please, the next slide. The trace gas orbiter by ESA and Roscosmos is dedicated to the measurements, mainly to the measurements of trace atmospheric species in the atmosphere of Mars. And it's particularly oriented on solar occultations, a method which is very sensitive to detect such a trace species. On board, next slide please. On board we have 4 instruments. 2 of them are European Nomad, and it's a solar occultation spectrometer, and Cassis, a camera, and two Russian Roscosmos provided instruments. ACS is a kind of it's very close to Nomad in goals, but different. And FRIEND is a collimated neutron detectors, a detector which is mostly the only instrument dedicated to the shallow subsurface of Mars on this orbiter. My talk will be concentrated on ACS. The next slide, please. ACS is a combination of 3 spectrometers to measure trace species, mostly in solar occultation, like this is shown on this slide. The geometry of solar occultation is very simple. You observe the sun through the atmosphere, and you can obtain directly profiles of atmospheric constituents. But unfortunately, you cannot measure to the very surface, because on Mars there is dust, mostly all the time, or clouds, which prevent to go down to the very surface. We have 3 channels in this instrument, 3 different spectrometers, including a Fourier spectrometer and 2 Echelle spectrometers, one with cross dispersion. It's quite a huge machine, 36 kilogram in total. In all, in this upper right corner of this figure, there is a spectral range of the instrument. It covers from nearly visible to nearly 20 microns. It's a broad range of in which many components, many gases and other atmospheric aerosols in the atmosphere can be characterized. The next slide, please. Here, just to give you an impression, it's a big satellite, telecommunication satellite used sent to Mars, and the instruments are in the upper part, just below this this cone, which was Schiaparelli, and you remember. The instruments are on the deck, and there are 4 instruments. 2 of them in black MLI, and 2 in a golden, and the 2 in golden MLI are the Roscosmos provided instruments. And the next slide, please. In in this talk, I will cover two scientific themes. First is is a bit hotter about the methane controversy and other trace species, and the second is more related to the topic of this workshop of this school, water and atmospheric dissipation, which is related to early Mars and to the processes which drove it to the current state. The next slide, please. First, about methane. Methane on the Earth is mainly biologically produced, and that makes people think that Mars is also a kind of indication of life on Mars. It's might be partially true, but not fully, because methane could be produced abiotically as well. And also it could be accumulated on Mars in collaterate storage, because conditions under the surface of Mars might be suitable for such compounds to be stable. Other possibility is that methane is released from volcanoes, because it's also a volcanic gas, but it's on Mars. Apparently, it's not accompanied by other abundant volcanic gases like sulfuric compounds. So it's a possibility, but not very likely. The current state of knowledge about methane is not about its origin. The next slide, please. It's rather about its variability and controversy between the measurements by TGO and by on the surface by curiosity. It's already 17 years when methane was positively detected on Mars and confirmed by different measurements. The papers by Formizana, Krasnopolsky, and Moma were published in early 2000. Then on the surface of Mars, Curiosity started measurements in 2011 and measured first no methane, then very little methane, then some spikes, and finally the kind of background level of methane, very small, which is shown here from 0.2 to 0.7 part per billion by volume, and which is a result which was published by Chris Webster with colleagues in 2018. One of Curiosity spikes was confirmed by measurements from the orbit by Marco Giurana with PFS. It's an interesting result, and one of the largest spike was published by Chris Webster and colleagues in astronomy astrophysics recently, about 20 parts per billion. That is these are other measurements. Next slide, please. And we are using the most sensitive channel to measure methane, which is ACS a Shelley cross dispersion spectrometer. The size of this box is about, well, it's more than half a meter in size, each dimension. And it measures several diffraction orders in one frame, and this series of diffraction orders can be put in any part of the spectral range. During one occultation, we have a sequence of spectra which is shown in the lower right panel of this slide. There we have pieces of spectrum, which each of them is one diffraction order, and the connected curves are spectra measured during different part of the occultation. From the transmission falls from 1 to 0 during the occultation season, or from if we go from below, it rises from 0 to 1. That's the source of information. The next slide, please. One diffraction order, one spectrum from that sequence corresponding to the most sensitive part, where the atmosphere is thick, but the signal is still high enough. Shows very tiny lines of H2O, but no CH4 lines. And the next slide, please. If we show one looking into one of these features, we can place maybe a guess about some positive detection, but that was never confirmed in any other features. And here we can place a very strict upper limit of 50 parts per trillion, 0.005 per billion. The next slide, please. Collected during 2 Martian years, these upper limits looks like that. No positive detection was done, and the curve of the bottom part of this cloud follows the season of Mars, because the dust content and aerosol content modulates somehow these detections. So on the same graph, we've put the upper limits, the background detected by Curiosity, and we can note that we are about almost 2 orders of magnitude below the upper limit. The background, the lowest. Hello? Yeah. Okay. Great. The lowest detections by Curiosity. The next slide, please. In summary, for what we can say for TGO search for methane, that after almost 2 Martian years of study, TGO confirms global absence of methane, and our best upper limits are about 20 pptv. We did a dedicated campaign near the Gizero Crater. There, conditions to detect are tougher because of in the equatorial region, and aerosols are always in place. There, the best upper limit is 65 parts per trillion, which is quite low indeed. there is an apparent controversy between TGO and MSL measurements. To say shortly, there are many studies dedicated to that, many studies involving models of mesoscale, including like local weather forecast, mesoscale models, and in implying these models, these models imply that to reconcile these measurements, the gale should be the only source of methane on Mars, and the emission should not last more than 10 or 20 years. That is considering that methane is stable on Mars, like all the models suggest, all the chemistry models suggest, or an unknown extraordinary mechanism to destruct methane is required to reduce its lifetime by a factor of 1,000, and this mechanism should not affect the other species, in particular active species like ozone or CO. Now we go to the next part of the talk, the second part of the talk. So next slide, please. I'm sorry. There on the positive side, of the trace species, we have a positive detection of new species, first ever by TGO, which is hydrogen chloride. The species has been searched from the ground with quite low upper limits, but it appeared that we detected it to be variable seasonally, and the detection is absolutely robust. We see 12 lines of different isotopes of HCl, Martian spectra. It appeared after the global dust storm in Martian year 34, the previous Martian year. They're almost in 36 now, and from the study we followed the seasonal trend, studied the correlation with water vapor and the isotopic ratio of that gas. What could be, from where could this gas come from? Possibly from surface dust, which that's suggested by its correlation with the dust storm, with the dust activity. But the mechanism is not very clear. It requires heterogeneous reactions. But also we can hypothesize some degassing, some activity from underground. The next slide, please. The follow-up studies showed that the gas reappeared in the following Martian year without much correlation with dust. Let's say because the Martian year 35 was much calmer in terms of the dust activity, and yet we have really few, but quite robust detection out of the dust activity in aphelion season where no dust is observed, and so this might be an argument favoring degassing hypothesis. The next slide, please. What is interesting, one study from our consortium used 1D photochemical model run in the context of Mars global circulation model, and they reproduced very nicely the measurements both in seasonal trend and the vertical profiles, but also they consider several reactions, including the organic methane chemistry, and demonstrate the destruction rate, increase of destruction rate up to 2,000 times. That is really a shocking result, but the paper is still in review, and some mechanisms which are included in that model might be still questionable. So let's wait and see how the atmospheric chemistry will explain this interesting suggestion. The next slide, please. Also, to show the to show the progress with in our spectral range, which I have shown the first result published in Nature about no methane. Now we can explain almost every giggle in this spectrum, which looked like noise in the previous slides, but now are absolutely new. There are multiple forbidden lines, magnetic dipole, field 2 band, and the next slide, please. The electric quadrupole band of CO2. These discoveries were possible because of that. CO2 atmosphere of Mars is a kind of a natural laboratory, a great, enormous mass of CO2 which can be used for such a to study such a tiny absorptions. The next slide, please. Now we go to the second theme of the talk, water and atmospheric dissipation. I won't be very long. There are many studies trying to extrapolate the escape on Mars back in time to estimate how much water or oxygen have left Mars during its history, to explain why it came to such a state that with degenerated atmosphere and almost very low amount of water. Please hit again the next slide. So the outcome of these studies, mostly the results from Mars Express and MAVEN, is that water loss can be explained up to several meters, several hundred meters of water, total global equivalent layer of water by different mechanisms, and up to 0.5 bars CO2. The next slide, please. We focus on one particular aspect of the hydrogen escape that was in focus of attention since maybe 2015-14, where people noticed that hydrogen escape is variable with season. Hydrogen corona, Lyman alpha measurements are vary with season, mostly noted from the ground from Earth orbiting observatories, UV observatories, and confirmed by MAVEN. I just to remind that Martian season is similar to that on the Earth, but asymmetric because the orbit is very eccentric. And well, recent yet unpublished data by Maven show that really the variability of hydrogen corona is really striking. The slide with Majd Mayasi showing her work with high resolution spectrograph measuring Lyman alpha, and she shows that the activity of hydrogen is increasing drastically during the perihelion season, when the Martian atmosphere is hotter and the dust activity is at maximum. Just to give a context. The next slide, please. We use another channel here mostly, but not only, but just to give a flavor. Actually, a spectrometer with acousto-optic filter for the selection. Here we don't have many orders at the time, but we have only one order, but we change them rapidly, and we can measure 10. We always measure 10 diffraction order per second, in interesting places of this near infrared spectrum. The spectral resolution is still very nice and allows for sensitive measurements. The next slide, please. The work, first I will present the work by Anna Fedorova and Denis Belayev, measuring accurate measurement of water vapor profiles together with temperature retrieved from CO2 absorptions, allowed to estimate the saturation state of water, and to note that the water is often supersaturated on Mars. There are two findings here, that water reaches 100 kilometers, and recently Denis just extended these detections to 120 kilometers during dusty season, and supersaturation on Mars is widespread. What does it mean? It means that on the cold region, the mesosphere, which on the Earth, where the cloud forms the cold trap for water. Water could not penetrate to higher altitudes, and where it could be dissociated. On Mars is not really very efficient, and the water can go through the colder regions in the atmosphere, and on the other hand, the atmosphere is getting hot enough up to high altitudes as well. So water goes much easily to high altitudes, and reaches altitude where the solar radiation is just destroying the water molecules and form the atoms which could escape to space. Next slide, please. This discovery was also illustrated in this nice paper by Mike Chaffin in Nature Astronomy, who used the data of 3 different spacecraft of Mars Reconnaissance Orbiter, MAVEN, and TGO to show that like this mechanism is working. Increased dust during just one small dust event, because not all the measurements were available during the major dust storm, for instance. He used a small dust event to show how from bottom panel up, dust is increased, the temperature is getting higher, and the clouds, the blue panel, are getting lower. Also, it is seen by camera on MAVEN and by ultraviolet images from MAVEN, and there TGO shows a drastic increase of water in the atmosphere. In the same time, the ultraviolet MRI measurements show the increase of hydrogen corona, all these measurements together. The next slide, please. That is the suggested mechanism, mostly the scheme advocated by Mike Chaffin, instead of previously accepted scheme of McElroy and Donahue, Parkinson and Hunton and Krasnopolsky is not mentioned here. The water should access to hydrogen should access to higher atmosphere through molecular hydrogen, involving very long-term reaction, and the other scheme allows direct water to access directly to levels of where it could be dissociated above 60, 70, 80 kilometers, and there it produces seasonally variable escape of hydrogen. The next slide, please. I have mentioned that we measure also the water up to 120 kilometers. This is a summary of the study, which shows that our point here that not only the dust storm, but mostly the seasonal effect. Every perihelion summer in the southern hemisphere forms the conditions for water to reach high altitudes and to escape easily, and this is shown quantitatively in this paper by Belayev, that near the perihelion season, water liftoff is nearly equal to that during a strong dust storm of Martian year 34, and given that the dust storm is relatively short and occurs only on this every third Martian year on average, or even maybe third or fourth, the seasonal effect is likely dominant. Next slide, please. We show that also using modeling, a simple air parcel model, but put in the context of measurements and model global circulation model. We show in figures that the impact of the dust storm is lower than the peripheral. The next slide, please. Also another way to assess how much water has been lost from Mars is to measure the deuterium to hydrogen ratio, or ratio of heavy, semi-heavy, and regular water on Mars. These are figures from paper by Geronimo Villanueva with a nice illustration that during the history on Mars, this is a scale in giga years, and the D/H ratio on Mars has been varying. This is a red curve, and the water inventory went sharply down first, and was then gradually decreasing even more. These are measurements from the present atmosphere and from different Martian meteorites and surface probes dated by Curiosity. Next slide, please. Here TGO contributed by first ever measurements by D/H profiles, and we were able to study how really in the atmosphere, how really both isotopes escape, and what are the mechanisms which regulate the fractionation. Is it condensation or photolysis or both? And these studies are published in nice journals. Mostly the results show the deuterium pose, the reduced D/H ratio up in upper parts of the profiles, which is predicted by models, but there are many details which are not predicted yet, and the models should be rectified. For instance, the winter polar region depleted in deuterium deteriorated water, and many details about the fractionation in the range of the cloud formation. The next slide, please. So this concludes my talk. Just to mention a few takeaways about methane, hydrogen chloride, and water. Just to note that these are fine but small selection of TGO findings. The next slide, please. We have many results which are published or being published now. The special section of GRL journals is being close to completion, and so well, please refer to some of this paper if you are interested, and I'm happy to answer the question if possible technically. Thank you very much for attention. And the next slide is just thank you.
So, Oleg, большое спасибо for your talk. Now I will be asking for some questions. Do you have any questions for Dr. Corral? So I'm going to ask you to come here just to make him hear your question. Sorry about that. I mean, just for technical reasons, we are connecting with Oleg via WhatsApp. So the audio is coming from WhatsApp. And we have some manual slide passing.
Hi Oleg, this is Lucia Marinangeli from Italy, and I'm a geologist, so I'm quite interested in the methane release from the subsurface. So my question is, are we missing some kind of investigation to better understand the methane cycle from the subsurface to the atmosphere? Do we need some different type of observation? It's quite unusual what you presented as a result from TGO. So I'm wondering if we need to think about a specific new type of investigation to better understand the methane cycle.
Yeah, many thanks for this question. This is an interesting topic. There is, there's a big debate about what's wrong with measurements of methane, because of course these new studies about the methane mixing and venting from Gizero Crater show that something really it's unrealistic that not only the methane should be not only Gale should be the only source to satisfy the TGO constraint, but also there should be the specific location of this putative source in Gale near the crater rim somewhere to satisfy the measurements of curiosity as well. There are interesting studies by Yuk Young group and published recently. What I think, what measurements I think would be important. We need more detectors on the surface of Mars. That's something quite. So far, there is only one TLS in SAM by Chris Webster. If we could put a second one or another one, another limitation of TLS is that it is measuring only a few times per year because of some limitation, and unfortunately there is no such an instrument in plan so far, but with new missions I think it's should be an important part. It could be a simplified package, not so sophisticated like sample analysis of Mars, but something simplified. In another thing I think which is missing is laboratory laboratory simulation about these putative processes that could destroy methane rapidly, because actually there is no for me. I respect deeply the work of Chris Webster group, and I think there is no reason to believe their measurements are wrong or something. There should be something unexpected in chemistry. Chemistry is a very complicated matter. Some reactions do go, others are not proceeding, and as we see, for instance, with the hydrogen chloride, nothing is conventional. Nothing is all reactions to explain need to be heterogeneous or something. It's a big work for laboratory confirmation. Yeah.
So thank you very much. Any more questions? Okay, so Oleg, thank you so much for being with us today, even if only virtually. So we expect to have a presential meeting in the following months or years. Who knows?
Yes. Hopefully, I think it will settle someday, and science could be together again.
Yeah, I hope so.
That's. I'm sorry I'm not with you, dear friends.
Don't worry.
Thank you for this opportunity again.
Okay. So thank you, Oleg. Bye. Well, we will end the session by now. We have a coffee break right there. We are going to signal the people from reception. And we're going to ask you just to enjoy some of the posters our students have brought, just to let you know their work. So we will tell you, I think in 15 minutes, 20 minutes, we will start the next session. Thank you so much. Let's get back to business.
I just take this one.
Okay.
And now then I need the... This one. Okay. Thanks, Lucy. Yeah.
Okay, so the next speaker is Professor Ari-Matti Harri from FMI, Finnish Meteorological Institute, and a very good friend of us. Thanks to him, we have get in contact with many other colleagues. So the floor is yours. Thank you very much for being here.
Thanks, Jose Luis. So I am Ari-Matti Harri from FMI, Finnish Meteorological Institute, and I lead a space research department at FMI. That's my formal task, and then my own let's say my most important area is Martian research, or planetary atmospheres, I'd like to say. So the scope of my talk, I try to firstly give an overview of atmospheric exploration, then to show, let's say, a glimpse of the various Mars missions that have been launched and they are operating just now, then discuss a little bit on the tools for exploration. So single in situ observations, network is mandatory, orbital support is mandatory. That's the scope. To start with, why Mars? Well, it's easy to access, let's say, among the planets, but it's a sister planet for us. There are so many similarities between Mars and the Earth, especially on the atmospheres. So there are two great similarities. Firstly, the tilt axis of Mars, the main tilt axis is about the same as that on the Earth. It's about 25, 24 degrees. Then the time of revolution of Mars around its axis is about the same as on Earth, about 24 hours. That's why the dynamics of the Martian atmosphere behaves in a very much similar fashion than that of the Earth. To the extent that we can actually transport atmospheric models and weather models from the Earth to Mars fairly easily, because the dynamic core is similar and programming that is a big task. We have made that for HIRLAM. HIRLAM is this weather forecasting model used in the Nordic countries and also in Spain and Switzerland in the past. Now there are new models, but still that was used for weather forecasting, and it's also running at Mars now. These similarities, they can be seen at Mars in the sense that we know that at the Earth we do have got the great cycling or great atmospheric flows consist of Hadley cycles from equator to mid-latitudes. There's Ferrel cycle in between, the polar area, and then the polar cycle. They are the large-scale flows at the Earth. In a similar fashion, also at Mars, we do have got the Hadley cycle, but not so much the other cycles. And then this large-scale flow at Mars is very strong. It's even stronger than at the Earth, because at Mars we don't have oceans, and that is why solar irradiation and the driving force from the sun is stronger. at Mars. But there are similarities, a lot of them. This shows where the seasons come. So at Mars we do have got similar kind of seasons as on the Earth. We do have got spring, summer, autumn and fall very clearly. That shows the way Mars is going around the Sun, and we can see the axial tilt is here. So when the axial tilt is this way, we do have got northern summer when we are sort of like facing the Sun. When we go to on the other side, we have northern winter but southern summer. The same ways as on the Earth, with the distinction that because the orbit of Mars is very elliptic, it means then that the northern winter is sort of like more harsh relative to other seasons than, for example, at the Earth, where we have circular orbit. But these similarities we have, and we can, that's why we can make use of similar kind of tools and methodologies than at the Earth. That helps us a little bit. Now, when we want to discuss and investigate Martian atmosphere, what do we need to measure and observe? We can go somewhere on the Martian surface and start observing and say that, okay, that's the answer. In a similar way as on the Earth, also this kind of simple, it's called primitive governing equations. You can find this on every textbook on the atmospheres. They are being used when we model the atmosphere, whether that's global circulation model covering the whole planet, or whether that's a regional model that covers, let's say, 20% of the planet or 40% of the planet. The similar kind of equations are being used. Of course, then there are lots of additions for local, to take care of local phenomena and topography and everything. So, but this is the simplest case. And that's lying there behind. Now, on these governing equations, you can see it's a partial differential set of equations. You can see pressure, various places. Then you can find there's well, pressure is the most important thing. Then that's also, then we have temperature all over, and that's driven by sun. And because it's driven by solar irradiation, then what comes into the picture is how well solar irradiation is reaching the planetary surface and the planet or the atmosphere. And there's dust. Martian dust plays a big role because it governs the solar irradiation, where it goes, how much of that is reaching the surface, how much is staying on the atmosphere, how much is reflecting away. This is why, if I remember correctly, I did. This is why we can say that most important observations is pressure and airborne dust. Airborne dust we can actually measure by measuring atmospheric thickness or opacity. Those are two major parameters that we need to observe, and that certainly has been done. Here we can see an old cycle of Martian pressure measured by Viking lander already. We can see how much the pressure is changing over a Martian year. This is one Martian year here. We can see that about 30% of the pressure, then it means 30% of the atmospheric mass is vanishing and coming back. Well, when it's vanishing, it goes into, it condenses onto the poles, and when it's coming back, it evaporates away from the poles. So we have these two parameters we need to observe. And this is just as example. It's like a beating, let's say, an engine that is beating very, very in rhythm, like heartbeat coming. And this is, it's 1 Martian day or so. Goes this way from on and on and on. The average pressure level is changing with season, of course. It's going up and down during the Martian year. But also, when we go from, let's say we are at the Martian summer, on various cases this is more regular beat, and then we go to the autumn and springtime, it starts having additional peaks, and it's more irregular. And this is one single observation. It tells us a lot. It tells us, I go back one slide. This is one single pressure observation. It gives us how the whole planet has done during the year. The evaporation from the southern and northern pole, condensing on those poles and so forth. Then on the other hand, a single observation tells us, this is from Gizero Crater from MSL, tells us nicely how diagonally during one day pressure is changing. And we have these small spikes here. They tell about the inflow and outflow of the gas from the crater. There's a flow over the rim of the crater. So at the night time, it's rushing into the crater, and at daytime, it's going back. So that's why we have this pressure cycle. One single measurement. That's why it's so important. But then, this is, as I said, from this example of Viking, so for the whole Martian year, we can get, again, a picture of the whole year from one observation. Here we can see two curves. One of them is Vikinglander 1, and one of this Vikinglander 2. And you can see there's a difference, so that this is higher pressure than this one, even if that's observed at the same time. Why would it be? Well, it's just because one of the landers, this one, is on lower altitude. And that's why pressure is higher than for the Vikinglander 1, it's on a higher altitude and pressure is lower. These were single observations made by a single observational post. It could be a lander, it could be a rover, even a small airplane, whatever. But most importantly, hopefully, they always measure pressure and optical opacity, or then airborne dust somehow. And but then, as we saw in these governing equations, that to solve them, we need those observational posts all over the planet. One site doesn't solve it. It tells about the big picture, and then it tells about what is taking place at the very spot where the observation is made. But it leaves the other areas untouched. That's why we need observations around the planet. And we need to cover, from the meteorological point of view, we need to cover the latitudes, basically climate zones. Let's say I talk about tropics, mid-latitudes, polar region, and then also on the poles. For longitudinal approach, this is at least 4 posts is needed. Altogether, we can get some 20 plus minus lander. That would be already good. Here I have just made a rough drawing of that. It's a Marsden map, and I have just landed some landers at Mars, as you can see. These are all landers. So we do have got a network mission, and we have put, as you can see, around equator area 1 and then mid-latitudes, polar regions. So that's why we have these 5 times 4, because 4 landers on longitude. Then I have added 1 at the Hellas, because Hellas Valley is very deep, more than 4 kilometers deep, and that exhibits meteorology of its own, as well as Tharsis area, the high ground area. So I have also added 1 there, and then 1 on the poles. So then we get more than 20, but it's, let's say, 20 plus minus something. This is a network mission that we have been talking about for a long, long time, and you may be aware of this this initiative that we did together with Louis and INTA and CAB, and there was also Lavochkin and Russian Space Research Institute from Russia. We had very, very good cooperation, all of the 4 of us on this. Unfortunately, finally, the final funding was not good enough for everything, and then we didn't get the launch finally. But the idea was to send. I just showed a network mission having these about 20-something individual landers at Mars operating simultaneously. Now, that was our aim, to start with a precursor mission and then to add into the full-blown network mission. And the background was in the work that was done in the past. Starting already from Mars 96, planning and development. So Mars 96 mission having 2 landing stations and 2 penetrators. It was a Russian mission with lots of Western participation. And FMI was investing heavily on that too. Then other Mars Polar Lander, Deep Space 2, Beagle 2, Phoenix Lander, all of those were something that contributed to the idea of MetNet network mission. The concept of the mission was like this. Instead of using parachutes, to use inflatable deceleration structures. And that was very innovative technology at that time, and it is now being pursued also, I will come back to that shortly, by ESA, but then also NASA has been working on that for some 20 years already, but for larger landing systems. But that was planned to have some 20 of these at Mars. It didn't materialize, but I want to underline this, that firstly, that this network mission really, it's important to get hold of the atmospheric dynamics and to understand Martian atmosphere properly. But then, to give weather forecasting and weather forecasting for large laboratories that very likely will be sent to Martian surface for Mars sample return or even manned flights. So we need to have a good weather forecast before we land or before we ascend also. So that is the rationale behind both crucial understanding of the Martian atmosphere, enhancing generally atmospheric science or planetary atmospheric science, and then weather forecasting. That's needed. But now then, as I in my title, when I talked about or mentioned about the continuation of MetNet, here we can see we have actually done a study together with INTA for ESA. This was an ESA-funded project a few years, so it ended last year. Actually, it started about we are doing the final reports. But the concept has changed a little bit to this kind of concept, but still it's a sort of like another branch of the MetNet concept, but it's still MetNet concept. We also have pursued the MetNet concept in terms of sort of like by payload precursors, so that we have developed derivatives of MetNet payload and flown them on board for firstly Phoenix mission, Curiosity, the failed ESA demonstrator mission in 2016, then Perseverance. All of them are carrying derivatives of MetNet payloads from FMI, from INTA mostly, and several from INTA. Right. Now then, in my talk, or in my title of my talk, I promised to talk about single observation and network missions, and then orbital support. And really, the orbital platforms are really important because they then are giving the big picture. This is what has been done recently. We from the left, we can start from landing missions of Pathfinder, MERS, so Opportunity, Spirit, Phoenix, Mars Science Laboratory, that's the same as Curiosity, the InSight and Perseverance. But then on the orbital side, we also have had very important orbiters like MGS, Mars Global Surveyor, Mars Odyssey, Mars Reconnaissance Orbiter, Mars Express, TGO, we heard a talk from Oleg, and so forth. So what do they provide? Like Mars Global Surveyor, it has been very important mission, not just for the general big picture, but also for all to understand the surface in situ observations. It has given firstly digital terrain maps, so the MOLA, laser altimeter, and then thermal emission spectrometer tests. So basically the maps that we see, they were originally from MOLA, from MGS, but now they are fine-tuned thanks to MRO, Mars Reconnaissance Orbiter, that is sort of like has continued the work of MGS. But as we understand, if we land somewhere, we need to know, do we land here on Hellas, that's with a depth of 4.5 kilometers compared to the surroundings, or on Tharsis area, that is very, very high ground. Or then that's needed because the atmospheric flows are greatly affected by this topography. Mars Odyssey, I just want to pinpoint this gamma ray spectrometer because it has given us understanding how much water there is at Mars. This is groundwater. The reddish color or the red-blue, that's for high water, high amount of water. or this whatever viola, and then there's less water on these areas. And Odyssey told us that when we go on high latitudes on both ends, both sides of both hemispheres, the amount of water in the surface layer, let's say 1 meter deep, is really something. There was a saying when these first results came that if you take a bucket of sand, somewhere deep, so let's say some tens of percent of that might be water. But anyways, there's huge amounts of water, especially here on the polar regions in the regolith. All of that information is given to us from Odyssey. Now when we observe somewhere pressure, temperature, humidity, wind, so it's a great asset to know what is the humidity reservoir around. Again, Mars Global Surveyor, MGS, and now is thermal emission spectrometer test. This might look difficult, but you just think that this is like dust optical depth. It means how much dust there is in the atmosphere, the topmost pane. Then the middle plane tells how much ice there is in the atmosphere, airborne ice, crystals of ice. Then the lowest pane, how much water vapor there is in the air. And this is a picture that this nice orbital platform gives us throughout the planet all the time, updating. So that is really, really wonderful. And then I just want to show this one more because to appreciate Viking. The Viking mission in 1970s, so it already had an orbiter, and there was a MAUD, atmospheric water instrument MAUD, so that together MAUD and MGS tests have actually given us the picture that we now have about how much there is atmospheric water there is and how does it evolve and so forth. Of course then later missions and later orbital missions like Mars Reconnaissance Orbiter has a CRISM instrument that has then added to this. But the basic work was done with these orbiters. I just want to appreciate the work of the past. Like this map shows where we have had missions. So Viking Lander 2 is here, Viking Lander 1 here on top of, let's say, just north of the Tharsis area. Recent landers, Mars Science Laboratory, were also instruments from us and various other organizations, ASBA, INTA, and FMI, are on board, is close to the equator. Perseverance, that was just sent 1 year, started operating 1.5 years ago. It is slightly to the left here, so that, as you can see, slightly north than Curiosity, and then different longitude. InSight is here. So we have got basically InSight and Curiosity. So this is now interesting because just now we have got 3 observation point posts working simultaneously. InSight and Perseverance, and then also and then Curiosity. Curiosity and InSight, they are on the equator, on both sides of the equator, about the equator. They are really, it's really nice to compare their observations. Then Perseverance is a little bit north and on the side, But very interesting science can be done out of these. So my team, we have been working on that quite a bit and publishing something. I actually plan to show something here, but I'm not allowed to because that's embargo still on those data before they are published. So as you know, NASA is very strict on these rules and we need to obey the rules. However, you can trust me that it is interesting to compare those observations together. So they are not a perfect network because they are too close to each other. But we can say that they are sort of like small regional network. So that kind of science we can do and investigations we can do with what we have now. Then still, because there are these other old landers that don't operate anymore, but the data is available. So some comparisons can be done even for those data if we take long means, so that certainly daily variation cannot be really compared, but long means, let's say few months, or then we can also compare the rough approximate evolution of, for example, diurnal pressure range over the year and so forth, from year to year. So that kind of comparison we can do. This is just to underline the fact that curiosity and insight, they operate close to each other around equator, and then Perseverance slightly norther. Then on the same latitudes we have Pathfinder, Perseverance, and also Viking 1. So that kind of similarities we can make use of. This is just to show the recent work. So Phoenix, Pathfinder, and then Curiosity and Perseverance, they look the same. So that's so on these landers we have instruments on board. We have had and INTA and FMI, and it has been very, very fruitful and interesting. When shortly going back to these observations, surface pressure, for example, to start with, we discussed this annual behavior of the surface pressure. That's on the top pane. But here we have got then diurnal pressure variation. That's measured by Pathfinder, where we can see interesting concepts like here, sudden drop of pressure, and it's actually, and this is actually a Phoenix observation. These are dust devils that we are observing at Mars in a similar fashion as we do observe them at the Earth. And the drop in the pressure, together with sometimes visual observation of the phenomenon by camera, and also simultaneous observation of large dust devils from orbit. So we can investigate these. I then said that the most important parameters to observe are pressure and airborne dust. But also, there are local variables for atmosphere and meteorology. Of course, temperature, humidity, wind direction, wind speed, at least. This is just to show for us typical surface temperature observation at the surface. Here we can see that's sort of like the surface temperature plot. Daytime it's high and nighttime goes down. But here we have three observations One of them is just at the close to surface. The other one is higher, around 1.5 meters. And then third one is in the middle. You can see easily what they are. You can see it's this way. You can see that here's the daytime and nighttime. So at daytime, surface temperatures go high, and at the nighttime, during strong inversion, surface temperatures go down. So then that's the surface temperature, this blue one. Then at the daytime, convection is high. So it means that, still, the temperature is highest at the surface layer, surface or close to surface, and then it's dropping when you go up. So this is the 1.5 meter temperatures here. So this just illustrates the fact that at Mars we do have got similar kind of situation as on a summer day in Sahara, for example. So powerful irradiation of energy at the daytime, strong convection, and then at the nighttime, very deep inversion, meaning that the ground is the coldest, again at the nighttime, because of emissivity. So it could be like from Sahara, but then of course the temperatures are different, but still, it's very interesting similarity. I skip this one to save some time. Now then, when we have the in-situ observations, we do have got orbital observations. We still need to couple them together, and the easiest way is to make it through modeling. As I said in the beginning, we can transfer Mars terrestrial weather models to Mars fairly easily. Easily in the hyphens, that it's not easy, as nothing is very easy when you go, but still it's much easier than to start from scratch, because the dynamic cores are similar. So we did it for Hirlam, that's this weather forecast model, and then currently more advanced models are Mars WRF. That's from this terrestrial WRF model. Weather research and forecasting model. It's a very regular model, or very often used atmospheric model or weather forecasting model at the Earth. But that also has been transferred to Mars. And then MRAMS is another one. MRAMS is sort of more like a regional model. And this Mars WRF is both global and regional. But they can be used to couple everything together. Here we see some observations. The actual observations we can see are these colored red and green colors. So these are from Martian sols at various times of a Martian year. And then we do have got we have modeled them with MRAMS is the blue one, then Mars WRF is the gray one here, and then Mars Climate Database. That's an open source database that anybody can access. You can go and access that and take the data. It's a database what has been created by using state-of-the-art atmospheric models. So anyways, we can see how the models nowadays actually behave very well. They can actually even, to a good extent, they can reproduce even a diurnal diurnal pressure variation, which is much more difficult than, for example, mean pressure over a year. So they are really a big asset nowadays, these models. The same ways we did for Gizero Crater in the past with our FMI's Hirla model, as I mentioned, we modeled the flow, atmospheric flows into and out of the crater. This shows the colors are temperatures, and this just shows both nighttime and then, no, this is actually nighttime situation where we are flowing. There's flow over the crater rim and then also flow from the Mount Sharp. But these arrows are or the direction of the flow and intensity of the flow. But by modeling, we can then expand the value of a single observation. Like Curiosity was making single observations here. Then we modeled the whole crater area and beyond. So when fitting that model into the observations by the single lander, we can learn a lot about the surroundings. So my conclusions or concluding remarks. Similarities help us. Similarities between Mars and the Earth. We can utilize similar kind of technology or methodologies and even models and instrumentation. So that's a great help. When we already have had a wealth of very, very good, excellent Mars missions that have given us long records of data already, and they have enhanced our understanding greatly of the Martian atmosphere. However, we still need the network mission, as we talked in the beginning, to get proper understanding of the Martian atmosphere, to really do new atmospheric science and then weather forecasts. And the weather forecasts are important for new expensive missions, whether landing laboratories or landing manned missions. And then interplay between in-situ observations, network, orbital platforms, and modeling is a key. Thank you.
So we have time for questions. Okay.
So, with the present situation around the exploration of the moon, do you think that we are going to have a stop in the Martian exploration or not?
Oh.
No, because actually it seems to be focalized,
Yeah.
mainly now in the moon. So it is a revival of the moon exploration. I don't know what is the driving force, but anyway, the question is that this year we have 3 missions, new missions in Mars.
Yeah. So basically you mean that because some focus really currently is on the moon research or lunar research, you are speculating that perhaps that's taking away resources from Mars. Well, that's a fair question. I think so. Hopefully that will add into the planetary science resources, hopefully. Then also, we know that NASA has this very ambitious moon mission, Artemis mission program for lunar gateway and lunar bases and everything. And then China and Russia also have their own plans for moon. So that's like there's a competition, rivalry, I think so. And it may take some resources, but actually I am optimistic. I think that perhaps that will just increase ambitions for space research and planetary research and actually add resources into this field. Also, as we know, NASA is talking about, as we know, about manned Mars missions and perhaps making use of the lunar gateway or this lunar activity, perhaps something on that front, perhaps, I don't know. But I'm optimistic still, so that hopefully there will be new resources because of this.
Okay. Any more questions? Oh. I'm sorry.
Harry, a curiosity, how long should the surface station in your MetNet idea, how long they should survive on the surface to get the necessary information for refine the model?
Thank you. So, minimum requirement is certainly 1 Martian year, because seasonal change is very dramatic at Mars. So seasonal conditions change. So that means that we need at least 1 full Martian year. Then, because we know that on every investigation and experiment, there are hiccups and so forth. So that's why I think we need several Martian years to really fulfill the objectives. So that's my wish. Several Martian years operating network mission, then perhaps supplementing the network later on subsequent launch windows, so that we could add more, and then that way perhaps replace some landers that are not performing very well and so forth. But several Martian years, hopefully.
We have one last question here.
Yeah, thank you. So I had a question about what you said regarding the detection of the water that is underneath the Martian surface, right? And then you spoke about using epithermal neutrons for that. So you guys use, I guess, the albedo effect to measure the possible abundance of water below that, right?
Yeah, so the gamma ray spectrometer, yeah.
Mm-hmm. Yeah. So now the following question is there any model, or you guys have developed any model to measure, to estimate the abundance of neutrons at the surface of Mars? Or does a model even exist? Or
yeah, there's GRS. That's a NASA mission, or what do you say? So actually, my team is not participating in that at all. I just showed the. So I must say I don't know that.
Okay. Yeah. Okay. Yeah, because I'm asking because.
But then, of course, there's a model. It is modeled, of course.
Yeah.
Yeah. But I don't know the details of that modeling.
Yeah, because in the community of radiation, there is this software named Atmorad that estimates the abundance of particles in the atmospheric environments depending on latitude and altitude and everything. And I don't know if such a model exists for Mars or not, or.
Very likely, yes. Yes, and it's needed, but we haven't used that.
Mm-hmm.
Yeah.
Okay, thank you.
Yeah.
So, Kiitos, thank you very
Gracias.
much for your talk. We will move to the next speaker, which is Dr. Dmitry Titov, who was head of.
Yes, the new retirement from ISA.
So we are very happy that you are enjoying your first month of retirement here.
Okay, yes. Can you hear me like this?
Yeah.
Yes.
Hold on,
sorry.
we have to load
Yes,
your
we have to
presentation.
change.
Yeah. Just 2 seconds.
And the pointer
Oh,
is
yeah.
over there.
Sure thing.
Good. Okay. Thank you. Okay. Thank you very much. First of all, thank you very much for inviting me to make this talk, because it's really exciting, and especially so many young faces here who will continue Mars exploration. As Jose Luis said, that the word former just appeared. It's less than 1 month ago. I retired from ESA and now being affiliated with Leiden Observatory, doing, well, I hope I will be doing similar science. So in this talk, I will try to entertain you with the recent and not very recent achievements of Mars Express, which is the pretty old missions from the standards of the space missions. It's already almost 20 years in flight, 20 years in orbit, working perfectly. So, and this is one of the most productive planetary missions of ESA so far. So I will go, but probably not many of you really remember that Mars Express is actually a Phoenix mission from the ill-fated Russian Mars 96 spacecraft, which plunged into ocean in November 96 due to malfunctioning of the propelling rocket. So European scientists, they contributed a lot to this Mars 96. And when it failed, they basically said, look, we spent a lot of time, we spent a lot of effort. We have already instruments which are on the spare parts on the shelves. Let's do something, probably a smaller scale, in Europe. So, and that's how Mars Express came into being. So basically, Mars Express accumulated the instruments which were arriving from the Mars 96 and added a little bit of those. Here is the list. So we have on Mars Express high-resolution stereo camera, stereo plus color. So basically, you can deliver the really wealth of information about the surface. We have the imaging spectrometer, which will look at the surface in different bands of different minerals and make the mineralogical mapping, telling us what was happening on the surface, which exposures do we see. We have a subsurface radar, which is called MARSIS, basically sounding down to about 1 kilometer, even down to, in some cases, 3-4 kilometers in the case of icy polar cap, and making the structure. We have the radio science instrument, which goes, it's conventional technique, doing the radio occultations with the ground station. We have several instruments to study the atmosphere. It's PCAM and planetary Fourier spectrometer. So PCAM is doing the solar occultation, and Oleg Korolev in the previous talk, he told about the occultation spectroscopy on trace gas orbiter. This is the precursor of that instrument. We have the particle instrument, who is detecting the plasma particles which are flying around the planet and basically sniffing and determining the escape of the molecules from the planet. And we just refurbished the visual monitoring camera, which was installed on board Mars Express just to see the Beagle lander to depart from Mars. Now we refurbished it into the science instrument, and I will show you what nice things can be done with that. Okay, with these spectrometers, Mars Express actually covering the science topics from the very top of the atmosphere in Aeronomy and evolution, then to the low and middle atmosphere, meteorology and climate, geology and history of the planet. And of course, we are doing Phobos. This is one of the not few missions that can do the flybys of Phobos. We are doing this regularly because of the elliptical orbit. So we have encounters with the moon at a distance up down to 50 kilometers. So let's go to the surface and geology. And so, first of all, looking at Earth and Mars. So this is the more or less comparison of these two planets. Mars is about twice as small as Earth. And what you see here is definitely, this is a dry planet, brownish, reddish color, with some veils of clouds here. What we see also, these are the polar caps and the poles. So to some extent, it is similar to Earth. To many extents, it's really very different from our planet. Well, the large-scale surface features you see here. So basically, this is the molar topography. Reddish here, this is the southern hemisphere, which is peppered by the craters, by the impact craters, meaning that this is old terrains, which are about 4 billion years old. Bluish color here, this is the northern hemisphere. They are much younger. It's about 2 billion years, and these are northern plains. So simply there are just few craters there. And we see Tarsis Bulge with several mighty volcanoes here. We see the Valles Marineris. We see the old impact bases, Hellas Basin. It's just the result of the impact in the early days of Mars. Really, it was a big planetesimal that hit the forming Mars. This is one of the exciting picture of Olympus Mons, the highest volcano in the solar system that was done by Mars Express high-resolution stereo camera. And it's really huge. You see here 22 kilometers to the top of the volcano. And with the scarp here, so about 8 kilometers. Can you imagine? This is just 8 kilometers down here. Well, if you put it on the map of Mars, this volcano will just cover, map of France, it will just cover the country completely. And if you compare it to our Earth volcanoes, they will look like just small hills at the profile of Olympus Mons. This is really a huge volcano. Well, it formed due to, as we expect, as modeling shows, due to the mantle plumes. When a big mantle plume rose up to the surface and really pushed the surface and formed these volcanoes. There are several volcanoes like this close to Olympus Mons. Well, another Valles Marineris, so it's a huge construction. So basically the Tarsis Bulge construction was so heavy that the surface could not carry it, and it cracked. So this is one of the rift zones with the length of a few thousand kilometers, the width of about 200 kilometers. Those of you who visited the Grand Canyon in the United States, so you can imagine that this formation is about 5 times larger in all dimensions. So really, this is huge, despite the planet is twice as small. Okay, so what do we see with the high-resolution stereo camera? These are just examples of the images. So when we can see, for instance, witnesses of early wet Mars, so some kind of, inhomogeneities here, which really tells us that there was wet Mars. We see the glaciers even in equatorial regions. These are typical glacier features which we see on Earth. This is not ice, this is dust. But in principle, you see that there was something floating, well, ice basically floating there. We see the remnants of the mega floods when there is a huge amounts of water where just for a short period were released and going and curving the surface. We see many tectonic features. So these kind of examples we can use really to study regional geology, the spatial resolution of about 12 meters per pixel. And what is important, chronology. This is an important word because we look at those places, we count craters, and we can derive how old is the surface. So basically, we can travel in space and time when we look at the images. For the moment, a bit less than 90% of the surface are covered by high-resolution stereo images of this type. And the eventual goal is to cover the whole surface of Mars with the digital elevation models, which is one example is shown here. So as you know, now we have the MOLA, laser altimeter topography with resolution of few hundred meters. So with this technique, with HRSC, we will do about 50 meters mean resolution all over the globe. So it's basically replacing or substituting MOLA. Well, interesting thing was found in the images. I think that this comes from early Viking, and this is HRSC. These are valley networks. If you look at this image, you clearly see house, something which we know about. So these are really rivers which were floating, which were on the surface of Mars long, long ago. And these are catastrophic floods with a lot of water involved. This is twice as interesting simply because physically water is not allowed to be present on the surface of Mars in the form of liquid. So simply the pressure is too low, temperature is too low. So water can be present either as a gas phase or as an ice. So it has the properties there like the dry ice, like CO2 ice on Earth. So basically you have not seen a glass of CO2. You know that there is a CO2 in the atmosphere, and you know that there are bricks of CO2 when we buy ice creams. But there is no glass of CO2. Okay, so and this is twice as intriguing what happened. And basically it shows us there was a water on Mars in the early past. Well, these are the remnants of the lakes that existed about 3.5 billion years ago. And here you see this is the bottom of the crater with the river which is coming into the bottom, and you can imagine, and there is a delta here with the deposition of the sediments just when the river enters the steady water. And you can imagine how it looked like billions of years ago. This is the place which we know now very well. This is Gizero Crater, and this is the river here. So, and there is a very nice delta in this Gizero Crater, and this oval, this pink oval, this is where the Perseverance rover is working now, collecting samples. So it's not by occasion this place was selected. It's simply because this place collected a lot of material brought with this ancient river into this lake. Okay, so I will try to show you the flight over Mars valleys. So basically, when you have a lot of images of the surface and images in stereo, you can design a digital elevation model. And with digital elevation model, you can do whatever you want. So you can fly, you can look at different direction, you can illuminate from different directions. And so this is now an example of one of the camera products. This is the Mars Valley. This was one of the candidates for landing on Mars. And so let's see. Okay, so this is how it looks like. This is composed from real pictures, real images of the high-resolution stereo camera, processed into the digital elevation models, and then you put a helicopter or whatever, and then you fly above this valley of this ancient river. Really very impressive products, and I like this very much. You feel like you are sitting on some kind of a helicopter and flying above the surface of Mars. Okay, so let's not... Yes, nice. Good, so let's go further. Yes, and from all these observations, we can derive the outflow channels distributions and valley networks. So basically the outflow channels, they are located here, they are in pink, in red, and the valley networks, they are located in this area and in yellow. Okay, now how geologists, Martian geologists work. So we have, as I showed you, we have the landscape which is coming from the stereo imaging. And also what is added, we know the mineralogy. Now the other instrument comes into play. We know mineralogy from what is shown here. These are spectra of different minerals and these characteristic peaks that tells us that hematite, for instance, phyllosilicates are present, etc., etc. So if you put this mineralogy on top of your topography, you will see the outcrops of different minerals. So you can analyze morphology plus your mineralogical context. And so from this you can really derive distribution of various minerals on the Martian surface. And then basically you have all information in hand really to understand how this particular formation formed, well, some millions or billions years ago. Well, for instance, this is the distribution of hydrated minerals that tells us where water was, again, billions of years ago. These are detections by Omega instrument, imaging spectrometer on board Mars Express, and also plus the CRISM spectrometer on board MRO NASA spacecraft. Good, so moving forward, so we have interesting formations like polar caps, 2 polar caps, and Arimati, and I think that, yes, he showed that these polar caps, they're really seasonal. It's like on Earth, you form on one in the winter hemisphere, then the polar cap is subliming on the, when summer comes, the composition of these polar caps was determined again by Mars Express. In the very early days of Mars Express, they looked at the polar cap in different spectral ranges. So, and basically what they found, what is shown in pink here, this is CO2 cover, several meters of CO2, on top of water ice, which is really sticking out of this CO2 cover here in blue. So basically, this was interesting discovery how the polar caps operate. Later, the high-resolution imaging from the NASA spacecraft came into being, and here you see really well, fine structure of these polar layer deposits. When you look at the troughs, then you see the fine structure. So these are the layers which were accumulated over millions and millions of years. This is a mixture of dust and ice. And let me, oops, okay. Then this is the view of the polar cap. Again, we have the digital elevation model. We can have an oblique view, so this is composed from real images. And with the surface penetrating radar MARSIS, we can really sound internal structure of the polar cap. And this is interesting because you clearly see here in the bottom of the polar cap, you clearly see the bedrock. And then you see a lot of layers in the polar cap. These are ancient deposits. Well, this allowed to derive the map of the polar cap. So when here you see the map of the thickness, and the thickness is from 4 kilometers at this deepest place to say almost 0 kilometers here around. And the total inventory of the ice is 1.6 million cubic kilometers, which is equivalent to about 10 meters of global ocean. Well, to take into account also that, to take into account that this is not full ice, so it's some of this volume is occupied by dust as well. But this is roughly order of magnitude. And so it's about half of the Greenland ice sheet. So this is how much water do we have accumulated in the polar caps of Mars. Well, recent discovery, just a couple of years ago, the MARSIS radar, it saw very bright reflections from the contact between the polar layer deposits and the bedrock. Really, the reflections were so bright that there was only one explanation, that there should be a liquid water over there. And this is one of the examples of the map of this region. And in blue, this is really strong reflections. Later, when the scientists analyzed, they found these reflections in many other places. These are, you see, distributed greenish dots. So one of the explanations is, yes, that there is a liquid water. And if it is salty and there is a pressure, because you have about several kilometers of the ice shield on top of you, there is a higher pressure and water can be in liquid form. Or there were other explanations like different minerals, salty, sand, etc., etc. So it's really enigmatic and very interesting, very challenging topic. But this was recent discovery, and with this we try always to say, okay, Mars Express is old, 20 years. But still, 2 years ago, just they used a little bit different mode of operations. They changed mode of operation of radar. And so that's why that allowed really to look in more detail, and they got really discovery that run through all the media, through all the science community. Okay, now we come to atmosphere and climate. So I think that Ari-Matti and also Oleg showed you this picture. I will just remind you. Well, the surface temperature, pressure is 6 millibar, is about 1% of what we have here. So the temperature goes down to minus 150, 140. Basically, this is the temperature of condensation of the main component of CO2 on Mars. And this is one of unique cases in the solar system when the main component of the atmosphere really condenses on the surface on the polar caps. And that's why, what again Ari-Matti showed you, that's why we see strong seasonal variations of pressure, because 1/3 of the atmosphere is condensing in the polar cap, and you can imagine 1/3 of the atmospheric mass is traveling from south to north and back every year, every season. Well, this is composition, 95% CO2, a little bit of nitrogen, oxygen, and water vapor. Water is very variable because it's a subject to many, many processes, from sublimation and condensation to adsorption by regolith. And what is important, again, I mentioned that liquid water is not really permitted to exist. So that's why when we see, for instance, these gullies with moving sand, it looks like water coming out, but there is a strong doubt that it can be. Okay, so again, this is seasonal. Mars is very atypical from many planets because it has very elliptic orbit. And when you have spring in the northern hemisphere, sorry, it's here, spring in the northern hemisphere. This is in aphelion. So Mars is receiving about 40% less solar energy because it's far from the sun. And this is the cold season for Mars. In this season, we see lots of veils of clouds, especially in equatorial region. While when we are close to the sun in perihelion, this is the summer around summer solstice in the southern hemisphere, and so there is a lot of heat coming from the sun, a lot of dynamic activity. This is where dust storms form. And so this is more stormy season, dusty season. Well, this is typical picture of the temperature field in the Martian atmosphere. This is pressure, or you can replace for altitude. This is the latitude range. It comes from the TESS experiment on the NASA spacecraft. But this is just to show you, yes, the temperature is decreasing when you go from bottom to top. The temperature reaches about 250 degrees Kelvin, even higher at the subsolar point in the south, because this is typical for the southern summer. And we have very deep polar night, very cold, where the CO2 ice is precipitating here. Okay, and these are the results that came from Mars Express. So each of these subpanel, well, it's difficult to read, but it's not about that you should go into detail. I will explain you. So each of these subpanel represents this certain property of the Martian atmosphere: water vapor abundance, ozone, oxygen, dust. And the bars, red bars, they separate different years. So you can, and vertical coordinate, this is the latitude. So basically, you can see how certain property evolve or change, the pattern changes from one year to the next year, etc. Well, you see common features, like for instance, for water, you see lots of water coming when you have sublimation of the polar cap, and this is reddish region here, here, and here, and here. But you see also differences between them. And this shows you the wealth of the Mars Express results and basically justifies that with such a complex system like atmosphere, which is dynamic, it's not enough to have a measurement for 1 month. You will not understand atmosphere. You need really to continue observations, monitoring for a long time. And this is one of the main difficulties to convince the space agencies to extend the mission, because they always telling, you are measuring the same property every year, and you're asking for another 3 years to measure the same. And the answer is yes, 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 because we are dealing with the dynamic system. If you do not do monitoring for a long time, you cannot really explain this. But of course, on top of this, we are trying to put cherries on the cake, like this discovery of the water underneath the polar cap. Okay, so this is one of the interesting annual cycles. I took just one box from the previous slide. And this is, again, latitude, this is season. And this is water vapor column here, as I said. When the polar cap is subliming, you have a lot of water coming out, and then the water is slowly distributing towards the south, and when there is a southern winter, water is accumulating in the other polar cap. But what is interesting, when you start measuring ozone together with the with water, and what you see, I can just blink between those. Ozone has the peak when you have the polar night. As soon as you come to springtime and water appears, basically there is no ozone. So there's really a chemical interaction between these two species. What is interesting that we tried to model, scientists who are working with this data, they tried to model, and they found that something does not match. So basically our models, they really do not produce behavior accurately. And interestingly, that the Earth models, they also failed to reproduce ozone layers in our atmosphere. So it's interesting that we have really coupling between different planets, and basically when the people study, they interact with each other and find some really interesting things. Okay, one of the interesting examples which was pronounced by Alec, I call it high water, that in the season, in perihelion season, when sun is close to, Mars is close to the sun, what is shown here, this is altitude, this is season, and in color, this is the water vapor abundance. And so basically what you see that when you go to the dusty season, warm season, in the southern summer, the atmosphere really expands, warms up and expands. And really homopause, which is usually sitting somewhere 20 kilometers, they really disappears, and water goes up into the levels of about 100 kilometers, 120 kilometers, from the levels from which it can escape. And we see exactly in that moment, hydrogen corona. This is the image taken by UV's instrument on MAVEN, NASA MAVEN mission. And these two teams, they are working together, and really interesting that, yes, we see this hydrogen which is provoked by the dusty warming, or by warming of the Martian atmosphere during the southern summer. Well, enigma of methane. Alec spent many slides. I will not repeat them, but just to remark that the first instruments to detect methane was planetary Fourier spectrometer on Mars Express. We all understood that this is really at the very limit of the detectability, because PFS has, well, it's called high resolution spectrometer, but it's not as high as required to detect methane. So that's why it was just one peak in the spectrum, which really gave some kind of tentative detection of methane with PFS. So, but we are proud that it was the beginning. At least it some kind of triggered interest of other astronomers to look at this. And you see, till now, we have this enigmatic discrepancy between different observations, enigmatic discrepancies between observations and modeling. So this is still an interesting and intriguing topic. Well, dust storms, this is the famous phenomenon. This is one of the images captured by HRSC camera. And you see just the front of dust propagating and covering the clear surface here. So this is the local image, but if you look with the visual monitoring camera, if you look, this was in August 2017, and year after, this is the dusty season on Mars. So you almost see nothing. You don't see the surface. Well, I couldn't stop myself from showing dust devils, because in the quiet conditions, it's always a question how dust can be lifted, because usually it should settle down and atmosphere should be quiet. And dust devils, which are ubiquitously observed on the surface of Mars, especially in the periods when you have high contrast, high temperature contrast in the summer. And this is, you see this beast, which is taken by high resolution camera, which gives a resolution with about 30 centimeter resolution of the surface. So you see here structure. HRSC also sees them with much poor resolution. And here you see it's just really, it can go into one of the picture galleries, and because it's really so nice. What is here? These are dark features, these are tracks of the dust devils on the light colored surface. Simply light dust is removed and you see like hairs here. So it's absolutely beautiful. And we have now lots of images from the Trace Gas Orbiter from the Cassis camera. Okay, another, remarkable thing was detected just recently with Mars Express, with this simple camera, which I told you was refurbished from the engineering camera. This is the long orographic cloud at Arsia Mons. So this is the image of taken by high resolution camera, the image of the Arsia Mons, one of the biggest volcanoes, which is up to, I think, 20 kilometers tall. And behind it, in the wake, there is a long, long cloud, which is located at about 40 kilometers altitude. Horizontal extension is up to 2,000 kilometers. So it's unbelievable, 2,000 kilometers. And you see, this is from the VMC camera, this is video, how they see it, just taking images one after another. You see this tail behind the Martian volcano. It's like it is smoking, and we still cannot understand why one of 5 Martian volcanoes shows this feature, and all 4, the other 4 are just nothing. So there are some explanations for that above the Arsia Mons you have interesting combination of conditions, of atmospheric conditions. What is shown here, this is the vertical coordinate, this is horizontal coordinate, and this black is topography. And color shows you the temperature field measured by planetary Fourier spectrometer. So, and basically above the volcano, you see high temperature, which is reasonable because your sun hits the surface. But higher up, at about exactly 30 to 40 kilometers, you see a cold pocket of air. I don't know what is the reason why it formed here. So, and basically, if you have a little bit of water and condensation nuclei, dust, light dust, you can form a cloud of particles here. And when there is a wind in this direction, you can get this structure. And interesting that structure forms just at the sunrise and disappears by lunchtime. So this is absolutely a fantastic and interesting result. Good. We go to Aeronomy and plasma environment. We see. In this field, we have a wealth of observations, first of all, of vertical structure of the ionosphere. This is just typical example that comes from the radio occultation. So ionosphere is measured from about 400 kilometers down to about 80 kilometers. And these peaks, they tell you about the ionization levels. So different wavelengths, they penetrate to different levels and ionize gases at certain level. And this is the day side, well-developed ionosphere. During the night, when there is no sun, the ionosphere quickly collapses and basically goes to zero, so nothing is seen. We could, let me see if I can. We also, due to the fact that Mars Express is going very close to the planet, about 250 kilometers, basically diving into the ionosphere. And each of those dots here, these are crossing of magnetic boundaries. So we can see topology of magnetic boundaries. We see how they depend on the external conditions like UV flux, like solar activity, et cetera, et cetera. So this slide, for instance, it was created on the basis of about 15,000 of these crossings. So it's really a lot, very rich data. And then also we could understand what is the response of the ionosphere to the magnetic field. So here you see the crustal magnetic field, this pattern, where the crustal magnetic field is mainly equator and southern hemisphere. And here you see excess of the total electron density as compared to the, say, standard nominal model of the ionosphere. And you see that this pattern really somehow resembles the magnetic field. So we really see that even the crustal magnetic field, which is pretty weak, it really has influence on the ionosphere, on the total electron density. Well, now we are coming to the question about the animation, about the ion escape. So we have, on Mars Express, there is a detector which measures the ions which are escaping from the planet. And because we're just flying through this media and really sniffing all these ions. So let me see if I can run it. It disappeared. Okay, I'll not touch. Okay, but it does not project here. I don't know. Okay, if it doesn't work, then we can just go to the. We can just go to the next slide, and there will be an. No. Oh, okay, yeah. All right, so this is the image which I grabbed from MAVEN, because Mars Express is working really densely with MAVEN, because we have Mars Express, it has a little bit different orbit, and okay, it's finished now, but actually what we saw here is really the ions which are escaping from the top of the atmosphere. And so if we go, could you please help me to go back to the presentation? Yes, and the next slide. I can turn it. Okay, so this is the picture ion escape. So this is basically the average escape. And you see these are magnetic boundaries, both shock and magnetic boundaries, which topology I showed you just on the previous slide. And this is where the ions, they are really leaving the planet. So when we can count those, and the result, this is the total escape flux from the planet, which is based on many, many observations. You cannot just make one observation. You have to fly many, many times through this soup of ions and electrons and measure them, and really to get the final number. And what we got to is that if you extrapolate back into history, then basically this can explain about 2 millibars of loss of the atmosphere, which is not enough, which is not a lot. So that's why the conclusion from the Mars Express observations was that the ion escape is basically not the major channel to lose the material. And then came MAVEN, and MAVEN really studied many other channels and really nailed down what is the how escape works at Mars. Just to illustrate, okay. This is the slide which shows results from MAVEN. This is the ion loss, oxygen loss from MAX. It's here. And apparently photochemical loss, just due to the fact that the molecules are bombarded by UV radiation, they are broken by UV light, and this is what is called photochemical loss. Those atoms or ions, they mainly escape. So basically, photochemical loss is one of the major sources. And if you really put everything together, so it seems that Mars has lost about 20-25 meters of the global ocean over its history. So at least this is how we see the measurements from MAVEN and Mars Express together, and really understand how much was lost. What is not taken into account, what is called hydrogen loss, when in the early phase there is a big hydrogen envelope of the young, very young forming planet, and there is just a hydrodynamic flow which removes not only hydrogen but also other species. It can be other channel, but which is not simply existing now, because planet basically lost all his mighty hydrogen atmosphere. Well, as I told you, Phobos observations, we have every 3-4 months, we have flybys of Phobos coming as close as 50 kilometers. We can come closer, but our engineers, they say, no, 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 the spacecraft will not be safe. So that's why 50 kilometers is our limit. So we can image a Phobos surface with a resolution of about few meters, which is already a lot. And now we're working with the JAXA MMX mission, which is to come and land on Phobos in 2025, approximately, because we are trying really to provide as much data as we can, and so that Japanese could prepare properly their landing and selection of the landing site. Well, now we're coming to the general picture, because the main, what is behind all these measurements, small pieces of the puzzle, is really to look at the big picture. What do these measurements tell us about evolution of the planet? What do they tell us in terms of comparative planetology? And well, first of all, this cannot be understood without the tools, databases, models, which are developed with the good participation from the Mars Express team, not alone, of course. And here are just examples. Very famous mass climate database, which was developed mainly by the scientists in Oxford and Paris. They do modeling. They model the meteorology of the current atmosphere, and they do modeling of climate. They go back to the ancient times, trying to look how Mars could look like. Then we have models of the plasma environment. We have visualization of the surface properties. Also, these tools are all available to the community. We have tools really for searching surface changes, because we have a lot of data with different resolutions in different times. So, but this tool can really compare the data, and you can see, aha, here's a new crater. Aha, here's the gully that really originated just 2 years ago. So we can do that and really look at dynamic Mars. It's not a frozen picture of the planet, it's really dynamic system. We can look at the global picture, because, as I said, we now know chronology to a large extent due to Mars Express effort. And so what is shown here, it's really schematic. This is time from the past, approximately formation of the planet and of the solar system. And this is the time when global dichotomy formed. So basically Mars is now composed of two parts: old, very old southern hemisphere and relatively young northern hemisphere. Each of those lines goes towards the present. Present is here. And the thickness of the lines, this is intensity of different processes. For instance, if you look at this time, this is the formation of the impact craters. This is the time when valley networks formed. It's about 3.5 billion years ago. This is where Tarsis Bulge started forming, so due to this plume. Then next period, the outflow channels these mighty outflow channels, which we still see on the surface, the disease of volcanism during this period, the canyons are formed, and then later you see some episodic volcanisms, glacial activities, polar layer deposits, etc., etc. So all this information basically coming from the really detailed observations by many orbital missions, and including, of course, Mars Express, because the camera, 10 meters resolution, is really occupying very good and very informative niche. So it's really regional geology, which tells us about large-scale and regional processes. Interesting, if we compare this time arrow to the time arrow of the Earth, which is here schematically, this is exactly the time when on our planet prokaryotes has formed. These are the first organisms were found at this, approximately at this period. And you see, if you look at Mars, this was the time when it was wet, when there was, for instance, outflows, when there was water on the surface. So basically, if we are so naive to assume that as soon as the boulders stop falling on our heads, life starts to emerge and blossom like it was on our planet here, then we can expect that similar happened on Mars. And this is really an interesting comparison because, yes, we still have a hope that if we will touch and if we will bring those samples, we will be able really to find some kind of paleo life on that planet as well. Good. So climatic models, they really, say 10 years ago, they were more optimistic. Oh, we see water flows on the surface. Geology tells us, so it means that Mars was warm and wet billions of years ago. But when we started modeling with our comprehensive models of climate, it was found that it's not so easy. We cannot really make the climate warm enough to have lots of liquid water in the early past. And this is still a difficulty. So when that what came instead of the warm and wet, like, I don't know, tropical paradise 3 billion years ago, what came into the minds of scientists is some kind of dry, Arctic-type climate. So with some kind of seasonal melting, freezing, melting, freezing. It's basically like we see in tundra of Canada or Russia. And so these are basically two options which are still now on the table. And we scientists are trying really to discriminate, do we see really evidences for this option or for that option. Good. Another comparative planetology issue which came from Mars Express and from its sister from Venus Express is that question, does magnetic field protect the planet? So till now we learned at the universities that we on Earth, we are happy, we are lucky because we have a well-developed magnetic field, intrinsic magnetic field of the planet, which is protecting us like an umbrella from the falling intensive solar wind. So that's why we are covered. But this would imply that the erosion of the Earth's atmosphere, for instance, oxygen losses, should be much lower than the oxygen losses on Venus and Mars, two planets that do not have intrinsic magnetic field. They're not protected, and they are just attacked directly by the solar wind. And here you see results of measurements. This is the escape rate. This is for Venus measurements, this is for Mars, and this is for Earth. And we see just opposite picture. We see that Earth is losing more ions, at least in ion channel of escape. It loses more material than Mars and Venus, which are not protected. So this is a big change in the paradigm. And so now the scientists really making some kind of, assumptions, ideas. Well, the main idea now is that the big magnetosphere of a planet, instead of protecting the planet, it actually increases the cross-section of the planet. And these cross-sections intersect a lot of energy which is coming from the sun. And this energy somehow is being transformed inside the magnetosphere and makes more energetic environment inside the magnetosphere that allows more ions to escape. But this is, you know, hand waving. So now people trying to make models, but still this is very interesting because this is really, these are measurements, and you have to explain those measurements. Okay, this is just, say, radiative transfer or energy balance considerations, which tells us that we on Earth are sitting just in 1 astronomical units. If you go a little bit to one side, you start freezing, you will get Mars. And if you get a little bit to another side, you start boiling, you get Venus. So what is how accurate is the tuning of nature? So basically, how lucky we are that really we're sitting in a very comfortable environment. So just a little bit to the right or to the left, and we are done, we are dead. So it's also interesting, and I think that we are having now more and more information from the exoplanets. Now we have discovered already 5,000 exoplanets. Probably they are not looking like our terrestrial planets, but we are approaching to this limit of small planets. And probably from those exosystems, we will really understand what is the probability to have this luck. And so you do not see the writings here, but this is really flotilla of the Mars missions, which was sent to Mars in recent time. Many orbiters, many surface elements, landers and rovers. Really, we have very intensive exploration of Mars. And yesterday, when I was in Prado, I thought that probably Mars should be really tired of really such number of guests, annoyed by such number of guests. And I think that Diego Velázquez 500 years ago, probably he foresaw that there will be lots of spacecraft coming. Good, but this is just a joke. I think that here I would like to thank you and stop here, and happy to have your questions. Thank you.
Thank you so much, Tima, really. Any questions for our speaker? Okay, just one, because we are going to lunch right now.
Yeah. Okay, so it is with the amount of information that you show here, this is great to summarize the whole mission. Do you expect with the present 3 missions some breakthrough or some new concept?
With the present missions?
Yeah, it is with the 3 new missions, NASA, China, and Emirates.
Well, I think yes. Well, I would not say probably breakthroughs, but as I said, so there is a big component that you need to study the system for a long time, really to make a long time series of observations. And from this viewpoint, I think that Arab Emirate mission, it produces very nicely the distant view, which was missing on our missions, because now all the spacecraft are trying to get as close as possible. No, but meteorology requires really sitting at the high orbit and looking at the whole planet, how it works. So this is the Arab Emirate. I think that they can do a perfect job here. China, their mission and their payload, it's very similar to what we have on Mars Express. And since Mars Express is really soon will be over, I think that Tianwen-1 will really take over, and they can do really very good things. And not forgetting that also while Tianwen-1 is there, Mars Express is there, Maven is there. So basically we have things, 3-point measurements, what is really very beneficial for plasma science. Because if you have one spacecraft in the solar wind and one spacecraft close to the planet in this inside magnetic boundaries, so you can see how the different parts of the system interact. Mm-hmm.
Okay, so thank you so much.
Good, thank you.
Yeah. So we'll return the session at 4 o'clock. So right now we need some energy to continue our travel to planet Mars.
Good.
So let's start with this afternoon session of our journey to Mars. And right now we have Professor Germán Martínez from LPI, from University of Michigan, and he is also a very good friend of us, but in particular he is one of our Spanish contacts at NASA. And I really would like to thank you, Germán, for the efforts that you're taking today, because we know it's 4th July there. Also being Spaniard, okay, but I mean, where do what the Romans do when we are at Rome. So right now, the floor is yours, so you can start whatever you want. Thank you so much.
Okay, thank you very much, Jose Luis. So, hi everyone. This is Germán Martínez from the Lunar and Planetary Institute in Houston, Texas. And I wanted to say first that it is a big pleasure to be here today and to be invited to give a talk in this summer course. So 14 or 15 years ago, I can't remember, but there was a similar summer course to this, also held in El Escorial in Madrid. And I remember that at that time I was an early PhD student, and it was very inspiring. I had a lot of fun during that week. It was also about Mars, and I really hope that like the students of the age that I had like 14 or 15 years ago can find this summer course as inspirational as I did. So having said that, the title of my presentation is Martian Climate and Meteorology, Future Missions and Challenges. And what I'll be doing today is to present an overview of the Mars climate based on in situ measurements, based on surface-based missions on Mars. I will also present the main knowledge gaps that we have related to the Mars climate. And finally, I will give a brief summary of the potential future missions to Mars. So what is next? Okay, so before getting into details, and since I cannot be there physically with you, for which I really apologize, I wish I could be there, but I wanted to give a quick self-introduction. So right now I'm working at the LPI here in Houston, but let me start when I was a PhD student in Universidad Complutense de Madrid in Spain. And so I was lucky enough to have Francisco Valero and Luis Vázquez as PhD advisors. That was the time when the MSL mission was being developed, the Mars Science Laboratory mission. As you know, the REMS is the weather station on board MSL, and Luis Vázquez, whom you know, but is here, like at the right of the picture, he was the principal investigator of that one, and I was lucky enough that he and Francisco Valero chose me as a PhD student. So that was the lift off for my Martian career. After that, I moved to Bergen in Norway. I moved to Michigan, where I spent 10 years at the University of Michigan, and I'm still related to the University of Michigan. And finally, I came down to Houston. So I am team member of the Mars Science Laboratory mission, and I am also co-principal investigator of the Mars 20 and 20 mission. And that's been pretty much my work for the last 10 years. I've done other things, but it's been mostly about analyzing weather, climate data returned from Mars 20 and 20 and MSL. So no more talking about me. I just wanted you to briefly know who I am. So let's go to the presentation itself. Okay, so I wanted to start the presentation by celebrating not only the 4th of July, which is Independence Day here in the US, but also the 25th anniversary of the first rover ever landed on Mars. So on this day, 25 years ago, the Pathfinder rover successfully landed on the surface of Mars. And this basically opened a new era of landers and rovers, and NASA, we've been continuously sending, we've had a continuous presence at the surface of Mars, since this rover. So yeah, I wanted to celebrate and remind this. So okay, let's start with the presentation itself. So why is it important to study the Martian climate? So the Mars exploration program is a science-based, technology-driven study of the red planet. It was funded in 1994, but anyway, something similar in NASA have been working for decades, and the Mars exploration program basically over decades has identified 4 main goals in the study of Mars. These goals are the search for life, understanding of geology and climate, and future human exploration. So as you can see, one of the 4 goals identified by the Mars exploration program is the climate of Mars. So this is how important climate is for the current exploration of Mars. And the climate is not a separate goal by itself, but it's also related to the goals of life, geology, and humans. Starting with life, it's important to understand, or when we want to identify past signs of life on Mars, or even potential current life, this life is intimately related to the current climate. We really need to understand the radiation doses. We really need to understand the weather environment to assess the potential of habitability and life nowadays. And same thing for the human exploration on Mars. So at some point, maybe the next decade, or maybe in next decades, we will be sending humans to Mars. The decade is not clear, but honestly, like I'm 40 years old. I really think that I'll be alive to see humans, like landing on Mars. So with this, I'm saying that this is something that will be happening in the next decades. And before sending humans to Mars, we really need to understand the climate, because we will need to predict the weather. So it will be important to make weather predictions, basically for the safety of the future human explorers. I'm pretty sure that most of you have watched the movie The Martian, and we don't want our astronauts to, we don't want them to go through the same thing as the main character, Matt Damon, in this movie. So anyway, hopefully this is how important the climate is in the study of Mars. Okay, so what has been NASA's strategy to fulfill these 4 goals, like geology, climate, and human exploration? So this strategy has evolved, but basically like 10 years ago, 20 years ago, the motto was follow the water, and the missions that we sent to Mars, like the driving force was to understand where was the water on Mars. Once we had a pretty good knowledge of, like the main reservoirs of water on Mars, the next step was to assess habitable environments. This was mostly done by the MSL Curiosity rover, and now, once we knew where the water is, once we know, or once we have assessed habitable environments, now we are on the 3rd step, which is seeking signs of life. And this is, like one of the main goals of the Mars 2020 exploration rover. So as you can see, this has been gradual. We have taken gradual steps. It has all revolved about the search for life. And again, for life, we need to know where the water is. Once we know where the water is, whether those places are habitable or not. And once we know where the water is, that those places might be habitable, then let's look for signs of life in those. So yeah, this has been the strategy. Okay, so how do we know about the Mars climate? So obviously, in addition to telescope measurements, like starting in previous centuries, and in addition to current modeling, Most of our knowledge of the Mars climate comes from missions, both orbital and in situ missions. So this is a pretty cool picture made by the Planetary Society showing the Mars exploration family portrait. And the important thing here to me is that around 50 missions have been sent to Mars, and it's not a trivial task. Around 40% of these missions have failed. So this is just telling us how difficult it is. Also, around 8 countries or institutions have sent missions to Mars. We have the former Soviet Union, USA, then Russia, China, Japan, European Space Agency, Emirates, India, and starting, I'll just give some highlights of this Mars exploration. The Mariner 4 in 1965 returned the first close-up images of the surface of Mars. Then in 1971, the Mariner 9 was the first orbiter going around Mars. In 1975, the Viking lander 1 and 2 were the first, surviving assets on the surface of Mars that were able to return data. And after the Vikings in the 70s, there was a shy period in the 80s. But then the golden age in the 60s came back at the end of the 90s, and pretty much since the last decade of the previous century, there's been a new golden era of the Mars exploration of Mars. We had the European Space Agency joining. We had India. We had the Emirates. So we are literally enjoying a second golden age, which has been enjoyed by private companies, and I'm sure with combined work from federal agencies and private companies, this will give a push to the Mars research. Okay, but here in this presentation, I'm going to talk about the Martian weather and climate from in situ measurements. So let me summarize the Mars surface missions that have returned meteorological data. Here you can see the map of Mars as a function of latitude and longitude, and then the color bar represents the elevation of the terrain. So the red and green colors imply high elevation, and the dark blue low elevation. So okay, let's start. The Viking lander 1 was the first lander on Mars. That was in 1976, and for over 40 years, it provided the most comprehensive meteorological data set from Mars. So that was huge. How much we could learn from the Viking 1 and also the Viking 2. You can see that they were working for pretty long. They surpassed expectations, and again, for over 40 years, this data have been the longest meteorological record on Mars. Then, 15 years later, on a day like this, 25 years ago, we had the Pathfinder landing, and which carried the first rover on Mars. That was a lander and a rover. The Pathfinder only lasted for 90 sols, if I will remember. But again, it was the first rover. Then we had the Spirit and Opportunity. The Spirit and Opportunity, same as the Pathfinder, were solar powered exactly. Spirit and Opportunity were operating for many years. You can see here the periods. There was a global dust storm that hit hard some of the instruments, But anyway, like it was, both brothers were working even after that storm. Then in 2008, we had the Phoenix lander. This was the first lander ever sent to the North Pole of Mars. It was also working with solar panels, and it lasted around 5 Earth months. Basically, it lasted for as long as the summertime lasted, because once we once we didn't have solar power anymore, like it couldn't go on. But it was like, like short period of time, but great discoveries for during those 5 months. Now in 2012, or since 2012, we have the Mars Science Laboratory, which is still working, as you know, and with all the instruments working on full steam. After the MSL, we had the InSight lander. The InSight is also operated by solar panels. MSL is not, and as I'll get to this later, but as you know, the InSight lander is now having power issues because there's a lot of dust deposited on the solar panels that are preventing nominal operations. But it's still alive, it's still there. More recently, we have the Mars 20 and 20 landed in February 2021, currently operating now, and I'm sure Arimati Harry this morning and Jose Antonio Manfredi tomorrow will give more details about this mission. And also the Tianwen-1, the Chinese mission joined, like the different rovers and landed on Mars in May 2021. So with all these missions, what are the typical meteorological data measured by this mission? So this is a packed table. I am aware of that. But what I want you to know, or what I want you to focus, is on the third column. So here you can see the main meteorological data taken by every mission sent to Mars. And as you can see, the pressure is basically the quantity that has been measured pretty much by every mission except for Spirit and Opportunity. This is not by chance, like, if you want to know about the weather or the climate in another planet, in another atmosphere, pressure is a very good quantity, because the pressure is telling you not just about the local conditions, but the pressure is telling you about what is going on at global scales. So this is why pressure has been present pretty much in every meteorological station. Air temperature and wind are also variables, or are quantities that have been measured in many missions. And again, like pressure, temperature, and wind, these are the quantities that you want to measure if you want to know about the climate on another planet. For the sake of history, I guess, I'll comment, or I'll say that the Spirit and Opportunity were the only missions. These are the Mars exploration rovers, A and B, Spirit and Opportunity. These are the only. This is the only mission that did not send a designated meteorological station. Every other mission sent to Mars had a dedicated meteorological station. We still love the Spirit and Opportunity. I'm not complaining. I'm just saying, like, this is how important climate is on Mars. But we always had weather packages. Still, Spirit and Opportunity carried mini tests, which was able to retrieve air temperatures. Now, basically, since the Mars Science Laboratory, the complexity and sophistication of the meteorological stations have increased significantly compared with previous meteorological stations, and you can see that MSL and Mars 20 and 20 are carrying the most sophisticated and complex weather stations ever sent to Mars. For the inside lander, I'll also say that the weather station is not as complex as the MSL Mars 20 and 20, but the inside lander for the time being has provided the longest record of wind measurements on Mars, if I'm not mistaken. So the inside lander, it's huge for the wind measurements that it has provided. And again, Mars 20 and 20, Jose Antonio Manfredi will be talking about it tomorrow, so I will not get into details. Okay, so what have we learned from all these missions, all these satellites about the Mars climate? What we've learned is that the Mars climate is governed or driven by three main cycles: the dust cycle, the CO2 cycle, and the water cycle. What I'm going to do now is to present or to show results for each of these three cycles based on in situ measurements for each of these missions. Let me start with the dust cycle. So the dust cycle, basically the way one can describe the dust cycle is that dust is lifted from the surface through dust devils and through wind shear, wind gusts. These dust devils are convective vortices on Mars that are visible because they lift dust from the surface, and these are pretty spectacular. These can be like kilometers high, and this is one way of inject dust in the atmosphere. Another way is through shear, through saltation of dust, like through winds. And then this dust is injected into the atmosphere. Through convection is transported higher in the atmosphere. And then it's transported horizontally or latitudinally. And then once the dust is in the atmosphere, the radiative effects of dust are huge. So we'll see that the dust cycle is literally the main cause of weather and climate on Mars. So we have weather on Mars mostly due to the dust cycle. Similarly to Earth, where we have weather, like we have lows and highs, typically due to water vapor. On Mars, this role is played by the dust cycle. So let me talk with data, with observations, and not with cool cartoons. Okay, so what am I showing here? So here I am showing the full record of aerosol opacity on the y-axis as a function of solar longitude for every single mission sent to Mars and for every single Martian year. So let me start with the figure, with the top left figure. This is showing the aerosol opacity as a function of solar longitude for the Viking 1 in green colors, and for the Viking 2 in gray colors. MY means Martian year 1213, and basically the Martian year is a convention that we follow on Mars, where basically it was imposed, established, and it's very handy. If I will remember, Martian year was 1950 something. I don't quite recall, but it's basically like how we count years on Mars. But anyway, let's focus on the figure. What you can see for Viking 1 and Viking 2 is a very marked. Well, let me define solar longitude very quickly. Maybe it was done, but for students or for people not familiar with Mars, this is important. So the solar longitude on Mars is a parameter that defines the time of the year on Mars, and then from 0 to 90, that means that we are in a springtime in the northern hemisphere. From 90 to 180, we are in summertime. 180 to 270 is fall, and 270 to 360 is winter time. So with this in mind, the main aspect that I wanted to comment on this figure is, first of all, between 0 and 180, as you can see, there's little variation in the water, in the dust opacity. And this is not only true for the Viking, but only for the MER A, which is here shown on the right, for the MER B, Spirit and Opportunity, and also for the, here on the bottom right figure, for the Mars Pathfinder, Phoenix, and MSL on Mars 20 and 20. So in every mission between Elsa 0 and 180, what we call the aphelion season, the interannual variability of dust opacity is very weak, and also the values of opacity themselves are pretty low. So this is why we call the aphelion season the clear season, because again, like values of opacity are very low, and this is why typically this is a good period to land assets on Mars. So it's the clear period when dust is not that high. However, take a look at what happens between 180 and 360. And let me, for instance, use this figure. So between 180 and 360, we have what we call the perihelion season. And during the perihelion season, as you can see, for every mission, the values of dust opacity are much higher, and also the interannual variability is much larger. Let me focus on the MER B figure here at the bottom left, where we have dust opacity for a bunch of Martian years from 26 to 33. And importantly, what you can see is that there are 4 periods with enhanced dust activity. The first period is the between Elizabeth, like 120 and 150, and you can see these peaks. This is called the Z period, and depending on the year, we might have dust activity or not. The second period of activity is the A period, and that's between 210 and 240. And you can see again that for every mission, MER B, Viking, MER A, MSL, Phoenix, we have like this peak in dust opacity around 220. Then from time to time, dust opacity can increase to very high levels, and this happens when we have global dust storms. Global dust storms are storms that encircle the whole planet, and these typically occur every 6 or 7 Martian years. So here during the Viking era, we had one global dust storm. Then that was in Martian year 12. Then in Martian year 28, and that was 2000 and I forgot, but like 15 years ago or so, we had another global dust storm where values of aerosol opacity, values above 4 were achieved. This was the Martian year 28 global dust storm here and here. Most recently, in 2018, we had the Martian global dust storm that was captured by MSL. And as you can see, typically these global dust storms, occur at about Elsa base 280, 270 for Viking, MERS. The one in Martian year 34 occurred a little bit earlier, but the point in this slide is so that you can see, the periods of main dust activity during the perihelion season and the repeatability of it. More things about the dust cycle. So how big is the particle? How big is the dust lifted from the surface? So here on the left, you can see a figure showing the particle, the dust radius, as a function of the solar longitude. And what you can see here on the left, I'm showing values in years with no global dust storms. So what you can see is that values are typically between 1 or 0.5 and 2 microns. There's some interannual variability, but this is about the size of dust on Mars. 1.5 micron is the canonical value. However, during the global dust storm in Martian year 34, and now take a look at the right figure, and take a look at the blue diamonds, we see that the radio particle size increased dramatically up to values of 6, 7, 8 microns. And this is very important before sending humans to Mars, and also very important for the machinery and sensors that we'll be sending to Mars, because the size of these particles matter for breathing, for lungs of the astronauts, and also for the machinery again. So these results are quite important. More on the dust cycle. So here on the left, what I'm showing is a parameter called dust correction factor as a function of solar longitude for spirit, opportunity, curiosity, and insight. And this is an important parameter. This is a parameter that basically, it represents the amount of dust deposited on surface assets. So let me start with, for instance, the InSight lander. The dust correction factor, well, in each figure, the black value represents the first year of operation, blue the second, and red the third year. So if we take a look at the InSight, started the missions here, and the dust factor was 1 because that's the beginning of the mission. That's a clear solar panel. But then as the mission progressed, the dust correction factor started to decrease because dust started to be deposited on the solar panels. And then at the end of first year, we go to, starts the second year, and it keeps decreasing. So this is important because there's a difference between, as you can see for InSight, the dust correction factor has been constantly decreasing, meaning that dust has been constantly being deposited on the solar panel. However, take a look at what happened with the Spirit and Opportunity. For Spirit and Opportunity, there were periods of time here around Elizabeth 270 for which the dust correction factor increased. And this means basically that dust was lifted, dust was removed from the solar panels of a Spirit or from the deck of the Curiosity rover, meaning that more solar flash, more solar energy was able to, to get to the Spirit solar panel. So, whereas for Spirit and Curiosity we had seasonal cleaning, well, Curiosity doesn't need the cleaning because we operate on nuclear energy. But still we have other assets where we can see this. But the important thing is Curiosity and Spirit underwent seasonal cleaning, InSight didn't. And why is this important? Well, unfortunately, you might have heard that InSight operations are, have been impacted by the lack of solar energy. And this is the reason, over time, the solar panels got dust deposited on top of them. And unfortunately, we didn't have events of dust lifting from the panels. We didn't have winds, or we didn't have dust devils that were able to remove this dust. So this is how important understanding the dust cycle is for future missions and human exploration. These are some knowledge gaps regarding the dust cycle. I encourage the audience to read a great report by Claire Newman in 2020, a white paper with the knowledge gaps. But let me move to the next cycle, as I only have 15 minutes here. So the next cycle is the CO2 cycle. Let me walk you, let me explain you this cycle based on this figure on the right. So what I'm showing here is the daily atmospheric pressure on the y-axis as a function of solar longitude, and then I'm using color code for the different Martian missions. So in green we have the Viking, in gray 1, in gray the Viking 2, and some other colors for some other missions. So I know it's a lot of color, but let's focus here on the important things. So first of all, you can see that for every mission, there are two relative maxima. There is a relative maxima around ELSA base 60, and there is an absolute maxima about ELSA base 250. The reason is that during northern summer and during southern hemisphere summer, the CO2 polar caps sublimate. And basically, the atmosphere gets thicker. There's more CO2 in the atmosphere, which is again sublimated off the polar caps. So that's why we have like this peak here. Then we have a absolute minimum at ELSA base 150, and this corresponds to winter time in the southern hemisphere. So this is the coldest time of the year. And basically during this time, the atmosphere in the southern hemisphere condensed onto the surface. And that's why we basically lose the atmosphere to the ground. And that's why we have this minimum at this ELSA base. Then here on this table, I'm showing, well, before going to this table, you can see that basically the sol-to-sol variation for every mission is stronger at about ELSA base 240 to 70. Here you can see like big sol-to-sol variation for the Vikings, even for the MSL. It's much stronger than during this time of the season. And the reason is that the perihelion season is where we have baroclinic disturbances. So in the same way as, you know, like in Madrid or Northern Hemisphere on Earth, we have baroclinic disturbances. We have like low pressures every 4, 5, 8 days. The same happens on Mars. And you can see the signal of that here in the pressure. And then, whereas, you know, like this ELSA base period is way more calm. And then I'm showing here the elevation for the different missions, because this is pretty much what explains the shift in these colors. So as you can see, the MSL is the elevation of the MSL or the depth of the MSL is the highest, and that's why we have like the largest values for MSL, because we have the largest amount of atmosphere on top of our heads. Then in cyan, you have the variability, you have the pressure for the Mars 20 and 20, and we have the lowest values because, as you can see here, it has the highest elevation. So basically, you know, this is sort of a elevation map, but the interannual or the subseasonal behavior is very similar for every mission. Okay, so let's move to the water cycle, the last cycle here of importance. So let me for the water cycle, let me start with this figure on the top left. So this figure, taken from Mike Smith 2005 paper. Sorry, I forgot to give him credit. So this figure is showing the latitude of Mars as a function of Martian year, and then the color bar is showing the amount of water vapor in the atmosphere. So what you can see is that every year there's a strong red color in the northern polar cap during summertime, and the reason is that in summertime the H2O ice, the water ice, is sublimated from the northern polar cap, and then it is transported in the atmosphere. And as you can see, it's transported towards lower latitudes. We have like a tongue of wet air. here, and then at the same time, in the other hemisphere, in the southern pole, which is wintertime, you cannot see it here, but basically the atmosphere is depleted of water vapor because it is condensed onto the surface. So that's regarding the water vapor. For the water ice, I'm showing here a similar figure, and this is showing in color the ice optical depth. And what you can see here is an important feature of the water ice is what we call the aphelion cloud belt. So take a look at what happens every summertime at about Elizabeth 90 at equatorial latitudes. We have this very strong formation of water ice clouds, and this is what we call the aphelion cloud belt. And as you can see here, I'm using orbital data, and I'm not using in situ data to give a global picture of the weather cycle. And this is not by chance. The reason is that we know way better about the water vapor due to global measurements than due to local measurements. And why is this? What's the reason? Well, in the water cycle, you can see that, like as I explained, water vapor is sublimated of the northern polar cap, but then it's transported in the atmosphere. But what is the role of the regolith? What is the role of the regolith in this weather cycle? The short answer is that we don't really know. Assessing the surface atmosphere water exchange remains a major unknown. So in this figure, what I'm showing is the different processes by which water can be exchanged between the surface and the atmosphere. And you can see that we have physisorption, salt hydration, brine formation, frost formation, and we really don't know, or we have not addressed each of these processes, which are really important, not just for the water cycle, but for the sake of habitability and brine formation, planetary protection, in situ resource utilization, and as I'll be showing next, this role remains still a little bit, not a little bit, remains quite open. Relevant to the water cycle, we have measured atmospheric relative humidity and ground temperature. These are the two key quantities that need to be analyzed to understand these four processes. And as you can see, the relative humidity and the ground temperature have not always been measured by the mission sent to Mars. So here on the right, I'm showing a table with, all the missions. And as you can see, ground temperature and relative humidity have been measured for the first time by the Phoenix mission, and then by the MSL and by the Mars 20 and 20. So these two data sets have provided us with the best knowledge of surface atmosphere exchange of water vapor. Let's take a look at these data sets. So here I'm showing the relative humidity measurements, all the data set ever measured from Mars. So we have values from the Phoenix on the left column, MSL, and Mars 20 and 20 on the right column. And we can ignore the first row. This is showing the coverage for each mission. But what you can see in the bottom row is figures of the relative humidity as a function of local true solar time for Phoenix, MSL, and Mars 20 and 20. And interestingly, what you can see for Phoenix and for MSL is that the atmospheric relative humidity has reached saturation level, so we have values above 100% for MSL and for Phoenix. Not quite yet for Mars 20 and 20, but now we are entering winter time. And then you can also see that during daytime, relative humidities for each mission are very low. So it's during nighttime when we reach high values. I'm going to, okay, I'm going to move here to water vapor estimations on Mars. So in the previous figure, I was showing relative humidity. Here, what I'm showing is water vapor volume mixing ratio, the total amount of water vapor that we have at the surface of Mars. And what you can see here on the left is that we have diurnal values for the VMR for the Phoenix mission. For the MSL mission, we do not have diurnal evolutions for this water content because the relative humidity was very low. And then for the Mars 20 and 20, here we have volume mixing ratio values for nighttime. We cannot estimate them for daytime, and that's what you see here, like the blank space. But we have values for nighttime. And the reason I'm showing VMR and relative humidity values is to show you the type of studies that we've done so far with these values. So let me talk about brines on Mars. So we have to have so that you don't get lost. What I'm going to do now is show you how we have used the relative humidity and VMR data to analyze brine formation and the other types of exchanges between the surface and the atmosphere. So for brines on Mars, we know that brines are basically salty solutions, liquid water with concentrated salt that can form via melting and the liquescence. Here I'm showing the typical, I'm sure you are familiar with this figure. These are droplets on the struts of the Phoenix lander that grew and evolved over time and that were hypothesized to be brines, so liquid water. And this is an example of brine formation analysis with the values that I showed you before. So here on the right, you can see temperature as a function of relative humidity for every mission on Mars. And for brines to form, we would like these colored symbols to be in this triangle. So the dashed colored lines represent the liquescence relative humidity for certain salts, for calcium perchlorates, and only when the relative humidity and temperature are within this triangle, the conditions are favorable for brine formation. What we can see here is that the conditions are maybe favorable for brine formation during short times, during short periods of the day. There's some overlap there. So we can say that, yeah, brines might form on Mars, but we don't really know whether kinetics would allow for this. In other words, if conditions are favorable during 10 minutes, are those 10 minutes long enough so that, like brines actually form? So we don't really know about that. Same thing for salt hydration. I'll go quicker here, but here I'm showing that the conditions of temperature and relative humidity are favorable for changes in the hydration state of certain salts that we have on Mars. But again, like, would kinetics allow for this during the short periods of times where we might have these transitions? Would this happen? That's something that we really don't know. And I'm going to move quickly here because I'm running out of time. And this is basically the last slide that I wanted to show about water vapor challenges. So here in this figure, I'm showing the main knowledge gap that we have for the water cycle. And in the figure, I'm showing the lab experiments in magenta, and as a function of temperature and relative humidity. And the important thing here is that lab experiments in magenta have been performed out of Mars relevant, have been typically been performed out of Mars relevant conditions, which are represented in cyan. So now we know that cyan is the Mars, like set of temperature and relative humidity values from these measurements. And typically we've been doing lab experiments at too warm temperatures or too dry conditions. So in order to better understand kinetics and the water cycle, we really need to push down these magenta values, and we really need to understand what's going on under most relevant Mars conditions. Finally, I just wanted to say that what we have ahead in the future is the Mars Sample Return and maybe the Mars Life Explorer. So these are two missions that have been highlighted in the Mars Decadal Survey. This is where NASA is going to focus efforts in the next decade to bring samples from Mars. And, this will be a very complex NASA and European Space Agency mission involving rockets, landers, maybe a lander fetch to fetch the samples from Mars 2020. It's quite complicated, but we hope that around early 2030s, that in about 10 years, we'll be able to bring back the samples from Mars. And finally, this is another mission that has been highlighted in the Decadal Survey. The Decadal Survey is basically a report that highlights and summarizes the main science challenges for the next decade. And NASA, and not NASA, but in the Decadal, and NASA will give a priority to these two missions, Sample Return and the Mars Life Explorer. The Mars Life Explorer is a different one, and will focus on finding current life and past life in low latitude regions. And this is what lies ahead, but I encourage everyone to read the Decadal Survey for further information. And this is all. Thank you very much, and hopefully my presentation made sense. Thank you. Thank you.
Okay, so thank you very much, Germán. Is there any questions to the speaker? Why not?
Germán, congratulations by your nice talk. But I found one thing that in no transparency I saw a formula. My question is that, are you anti-mathematician now, or really, or are you studying some fitting, some formulas, some equation to study the evolution of the dust, for instance?
That's if I have to be honest, after 11 years after 12 years in the US, gradually I stopped to use equations and formulas in my presentations. I stopped using LaTeX in favor of other software. So what I'm saying, Luis, is I'm guessing you are totally right, and but for some reason when I show equations, it depends on the audience, but on this side of the Atlantic, you are right, Luis. Yeah.
Germán, if you want to activate the webcam so everybody can see you.
Oh, sure.
No problem. Okay.
Yeah, you can see my empty office. I came back to my office after 2 years, during the pandemic, so that's why.
Well, it's something like what future Martian astronauts will find when habitat is built.
Yep.
Any more questions for Germán? Okay, again, Germán, thank you so much for being here with us, really.
My pleasure. Thank you very much to everyone, and a big hug to everyone, and thank you. Thank you.
So the next speaker is connected right now. Oh, okay. So hi, Dimitra. We can see you right now. So Professor Dimitra Atri is, oh, okay. That was a good one. So Professor Dimitra Atri is from New York University at Abu Dhabi. We're very happy to have him here, even if it's virtually, because we had some bureaucratic problems to bring him here, and we have to blame our embassy. This is what we have to say publicly. Especially, we are very happy to have him here because it's about 1 year that our university signed a contract, an agreement with his university to participate in the HOPE mission. And during this year, we have some ongoing works, but what Professor Atri is going to show you today is going to be really, really mind-blowing. So the floor is yours.
Yeah, thanks so much. Thanks for the invitation. I hope you're able to hear me clearly. Can you hear me?
Yes, we can hear you.
Great, excellent. Hi, so I am Dimitra Atri, and today I will be talking about exploring Mars with the Emirates Mars mission or the HOPE probe. All right, so in case you are wondering, University originally started in New York, as you know, and now it's a big global network of universities. So in addition to a campus in New York, it has now a campus in Abu Dhabi and in Shanghai. So I'm based at NYU's campus in Abu Dhabi. And an interesting connection with Mars is that in each of the countries where NYU's campus is based at, there was a mission launched in 2020, as you all know. So the first one to launch was the HOPE probe, which is here in the UAE. Then the other two missions are Mars 2020 from the US, and then the Tianwen-1 and Zhurong rover by China. So let me tell you that UAE is just a short drive away from you, and so yeah, feel free to stop by whenever you want. It's a very young country. It was founded on December 2nd, 1971. So just 51 years ago, very young country. The interesting thing is that on the same day, the Soviet Mars 3 mission entered the orbit, and it was the first successful soft landing on the surface of Mars. Although the probe lost contact, so it couldn't do any science. But anyway, it was a historic day that way too. It's a very small country with a population of 10 million. Unlike other countries where you have, a small fraction of the population is expats, here majority of the population, 90% of the people are from the outside, like me. It has a very active space program, and everything is very new. So the UAE Space Agency, Mohammed bin Rashid Space Center, MBRSC, and the Center for Space Science, where I work, are all less than 10 years old. So let me tell you a bit about UAE's space program. Just recently in 2019, UAE launched its first astronaut for a mission on board the International Space Station. Then next year, the HOPE mission was launched. Later this year, there will be a lunar mission. There will be a rover called Rashid, which will be launched in October. Then next year, one astronaut is going for a 6-month mission on the International Space Station. So a lot of opportunities for us to do microgravity research. Then in 2028, there is an asteroid belt mission with flyby of Venus. And there is another very interesting project called Mars 2117. And the idea is to establish a human base on Mars by the year 2117, which is a project to continue research on Mars, plus inspire the young generation to study science, to study space science and technology, and build careers in those areas. All right. So let me tell you a bit about my research here. So I lead the Mars group here, but I do many more things. So one of our main focuses is to study the atmosphere of Mars using HOPE and MAVEN. And on the left, you see our researchers who are a very important component of this. So our idea is that a combination of HOPE and MAVEN can allow us to study many things in more detail. For example, auroras, atmospheric escape, and so on. The thing with HOPE, as I will tell you more, is that it is so far away from Mars that it gets global coverage, which is not possible in other mission. And we also have a collaboration with UCM, and in addition to using Mars Express and other data, we also intend to use machine learning, which I think is severely underexplored in planetary sciences in general. All right. So another project is experimental work. So in addition to studying the atmosphere of Mars, back in the day, about 1.5 years ago, I was very excited about the upcoming ExoMars mission, which was supposed to drill 2 meters deep. And I was doing some calculations about what kind of chemical environment would be there and whether it could support biological activity or not. Then I got in touch with the chemistry lab here, and then we started this lab where we are basically simulating Martian conditions. One of the projects we are focusing on is to test different types of organics on Mars, to study the degradation rate in harsh conditions with cold temperatures, UV radiation, presence of oxidizers such as perchlorates, and studying their stability. Another thing we are doing is, which can be described as a theme of habitability in space, which means that human habitability, which is space travel as well as settlement on other planets such as Mars, as well as microbial habitability, so which objects in the solar system could support microbial life as we know it. So here on the left are our group members, and you can also consider this human phantom a group member because it endures a lot of radiation, which we use to do our calculations. So we do a lot of work. We model radiation dose on the surface of Mars, radiation dose on astronauts while they are in transit on the Martian surface. And we can calculate radiation dose deposited in different organs of the human body and then compare with medical literature. We also use data from the RAD instrument onboard Curiosity for calibrating our model. So on the right, you just see one example where we have calculated radiation dose on the surface. This is something very new, and this is exploring Mars analog sites. So Vignesh, he just finished his master's degree, and he was working in our lab. And one of his passions, he's a geoscientist, and one of his passions is doing field work. And he did field work here in Abu Dhabi and in India, and he got really interesting results. So this is something very new for us. So this is just an overview of the kind of work that we do here. Um, Let us come back to the atmosphere of Mars. A number of speakers earlier today gave you a very good introduction about a number of problems that we need to understand when it comes to Mars. So I will be brief. So one of the main things to understand is how did Mars lost a majority of its atmosphere. The atmosphere eroded over a period of time. So how did that happen? So NASA's MAVEN mission has unique set of instruments to study atmospheric escape. So the figure that you see on the right hand side, you can see the complexity of process. There are a number of channels through which escape occurs, and it's a very complex problem. So with MAVEN, we get data from both UV monitor, so solar UV, as well as it has a number of instruments to detect charged particles. Plus, it also has a magnetometer so that you can measure magnetic field, and it's an excellent instrument to study this, especially the connection between space weather, activity of the sun, and the Martian upper atmosphere and exosphere. Now, one of the main disadvantages of MAVEN, which I'm going to quote Bruce Wikoski, who used to be the PI of MAVEN, from his science paper, that we cannot reliably provide a global escape rate during the ICME event based on these sparse observations alone, owing to the limited coverage over a short period of time. So this was a paper in which there was an interplanetary coronal mass ejection, so basically a plasma from the sun hitting Mars, and atmospheric escape increased, which was observed, and this paper showed that. But the data was only from a very small fraction of the planet, and measurements were made only for a short period of time. And that is because, as speakers before me showed, that everyone tries to go as close as Mars as possible, and so that you get excellent data. However, the coverage is small. So this is one major disadvantage of a mission like MAVEN. I can make the same case about other missions. And so the idea is, okay, can we have a mission which can fill the gap? It can do something different to solve this problem. And so the Emirates Mars mission, or HOPE, was commissioned because of this. It was conceived very recently in early 2014. It was announced in mid-July. It is a collaboration between the UAE and the US. US, as you know, has a very long history in Mars exploration, so it was a perfect partner. Now, on the right, you see the figure. You see Mars, and you see in red major missions, and you see that they are so close to the planet. And HOPE, on the other hand, is much further away. It is even further away than the Phobos and Deimos's orbit, satellites of Mars. So the orbit is 20,000 by 43,000 kilometers with an inclination of 25 degrees. The orbital period is about 55 hours or 2.25 sols. One orbit covers about 1/4 of the planet, 90 degrees. So you need four orbits to get a full picture of the planet. So what are the science goals? So the UAE government went to MEPAG, which is the Mars Exploration Program Analysis Group, to find out what kind of science goals should we look at. And so the three major science questions which were agreed upon is how does the Martian lower atmosphere respond globally, diurnally and seasonally to solar forcing? So a connection between the lower atmosphere and upper atmosphere. How do conditions throughout the Martian atmosphere affect rates of atmospheric escape? And how do key constituents in the Martian exosphere behave temporally and spatially? And based on these three major science questions, you can narrow it down to major science objectives and then major science investigations which will be carried out. So one of the main investigations is to determine the 3D thermal state of the lower atmosphere and its diurnal variability on sub-seasonal timescales. And so this is the key behind MAVEN, that you can observe things, you can see diurnal variability, you can see how things change on sub-seasonal timescales. In order to solve these problems, HOPE has three instruments on board it. So one is EMIRS, which is the infrared spectrometer. Then you have the UV instrument called EMUS, and it has a camera, an imaging camera, 12 megapixel called EXI. So you have both visual, UV, and infrared to study all of these things. And I will talk more in detail about these. So to give you just a big picture, a summary of what HOPE can observe, and it is to get a full 360 view of the planet. So let us start from the surface. It can give you the surface temperature, clouds, both water ice clouds, CO2 clouds, dust, atmospheric temperature, water vapor, ozone. And if you are a climate person, then this is a gold mine for you. Then let's move upward to thermosphere. In the thermosphere, you can observe carbon monoxide and neutral oxygen. And much further away, you can look at neutral oxygen and neutral hydrogen in the exosphere. So let me give you some historical context why it is such a big deal for the UAE. So if you look at Mars exploration in the 20th century, it had two players in the field, United States and USSR, which launched a number of missions. Then in the 21st century, ESA launched its first missions and others followed. And after that, India launched its orbiter around Mars. So it was a very, very small community, a very exclusive club. And then in 2021, you had two new players, UAE and China. So it was a really huge deal for such a young country, such a small country. And I would regard this as an Apollo moment for the UAE, because media coverage was wall to wall. You could not get anything else on television, in newspapers, in radio, on internet. It was all HOPE mission during launch and when it reached Mars. So it was a very exciting time. So on the left, and everything was followed live by TV crews. So on the left, you can see the HOPE probe during its final testing and so on. On the right, you see this probe was packed because it was launched from Japan. So you see a TV crew following HOPE mission through the highway of Dubai. You can see the part of the desert in the background. And then it was loaded in this aircraft to take it to Japan. And it was at the height of COVID during the lockdown phase. So that was another major hurdle. But finally, there were weather issues and so on, and the first launch was scrapped. But then finally on July 20th, it had a spectacular launch from Japan. And after several months, it reached Mars on February 9th, 2021. Here is the ceremony where we actually came to know that Hope has successfully entered Mars. And on the left, you can see that I am standing there in the middle of all the cabinet ministers and all the top officials of the UAE. And so it was a very different environment that I was used to. Anyway, it was a very exciting moment. This is just a bunch of other photographs. On the left, you see the full instrument, the probe with all the different instruments. It is of the size of a small car, 550 kilograms, and now it is orbiting Mars. So let me talk about these different instruments. And as I told you, these instruments were made in collaboration with different institutes in the US. So this EMUS is the Emirates Mars Ultraviolet Spectrometer, and it was made in collaboration with CU Boulder, University of Colorado, with LASP, and they were also the ones to build the first ever UV spectrometer on board Mariner 9, which orbited Mars. So it is the same lab. It measures emissions in spectral range of 100 to 170 nanometers. It has a spatial resolution of less than 300 kilometers, and it is good enough to characterize spatial variability in the thermosphere, so which is about 100 to 200 kilometer band, and the exosphere, which is 200 kilometers and above. So in the thermosphere, it gives the column abundance of atomic oxygen and carbon monoxide. And in the exosphere, it will give the density of atomic oxygen and atomic hydrogen with both spatial and subseasonal variability. So it gives you the full picture. On left, you see the EMUS instrument, and then at the bottom you can see all the different things such as Lyman alpha, Lyman beta, argon, and other things which you can identify from the spectrum. The instrument has a number of observing modes, so you can see right from the thermosphere all the way to the outer exosphere, and the data is organized in this way. So you have data from the outer exosphere, which is beyond 6 Martian radii, the middle exosphere, which is between 1.6 to 6 radii, the inner exosphere, and the thermosphere. So data all the way out to several Martian radii is available. The next instrument is EMERS, which is an infrared spectrometer. It was made in collaboration with the Arizona State University and Northern Arizona University. And as you can guess, that infrared spectrometer, it is used to determine the 3D thermal state of the lower atmosphere and its diurnal and seasonal variability as expected from all things Hope. So on the left, you can see the synthetic spectra, the different colors you see. You can see how things look during daytime, at nighttime, during dust storm, during thick clouds. So this EMERS, as I mentioned earlier, is an FTIR spectrometer covering a range from 6 to 100 microns. It can give you the column integrated abundance of atmospheric water vapor, dust, water ice opacities. It can give you temperature profile using the CO2 absorption feature at 15 micron, which you see here. It can also give you the atmospherically corrected surface temperatures. So a lot of data comes from this instrument. And then finally, the third instrument is the EXI instrument, which is the Emirates Exploration Imager instrument. It has two telescopes. One is UV and one is the visible one. So it acquires full disk images with a resolution of 2 to 4 kilometers per pixel. These are the number of wavelength bands, so going from 220 nanometers all the way to the red band, which is 635 nanometers. As I mentioned earlier, it can detect clouds, but it can't distinguish between water ice and CO2 ice clouds. So some extra work goes into that. And then this is a great instrument to study dust storms, thermal inertia, and with limb observations, you can do a lot of things. All right. So as I mentioned earlier, that in one observation, it covers about, in one orbit, it covers about 1/4 of the planet. And so here you can see that how it integrates data over a period of time. So on the top one, you see that you have the time intervals divided in 3-hour bins. So midnight to 3, 3 to 6, 6 to 9, and so on. And then on the horizontal axis, you have the number of days. And yellow is the coverage. So this is from the EMIRS instrument. And you can clearly see that from day to day, it covers a chunk of Mars. It records that data. And if you add it up, which is shown in the bottom figure, you can see as you move. So on the left, you see you don't have much coverage at all local times. But if you move towards the right, you add more and more data. And you can see on days 9 and 10, you get pretty much the full coverage except the polar regions of the whole planet, and which is the key behind this mission. Now, because it gives you the full coverage, it is possible to get around the clock coverage of most parts of Mars. So I thought, well, there are two instruments, and our earlier speaker, Herman, and then you have Jose Antonio in the crowd. Both know about these rovers intimately, and they give surface temperatures. So the idea was to compare the temperature that you obtain from the HOPE probe from the orbit, so from 20,000 to 43,000 kilometers away, and what you measure from the surface. Now, comparing anything, comparing data between two missions is tricky anyway, but comparing data between an orbiter and rover is extremely tricky. And so what I'm going to show you is just our first attempt in trying to do so. And so we took this data from the month of July. So the HOPE probe started its science phase in May, and there were a lot of adjustments and so on. So you started seeing good data coming in from July. So we had good coverage from July 2021. So in this plot, you see this is the full map of Mars. So minus 90 to plus 90, minus 180 to plus 180. And these colors are surface temperature from HOPE. So blue is cold, red is hot. And these are the locations of the two rovers, Curiosity and Perseverance. And the idea was to compare them. And these are the group members. So we have the round-the-clock global coverage. So you take, just like earlier, you take 3-hour bins, you get full global coverage, and you can see in any time slot how the temperature varies throughout Mars. And this is all local time. And if you look through different time slots, you can see that as you move from colder temperatures. So at night time from 2 to 5, 5 to 8, 8 to 11, and so on. As the day goes, you can see how Mars is heating up and then it cools down. So this is a comparison, a direct comparison between the measurements. This is taken between L sub s of 65.8 to 73.9, so about 30 sols. So Curiosity rover has this REMS instrument, which you heard about from the previous speaker. You see REMS data in blue and data from the EMIRS instrument on board HOPE in red. And below you see this from the MEDA instrument, these measurements, and HOPE measurements are in red. Now, this is from our earlier phase of analysis, which we put on archive, but we have revised this. We now have a better way to clean this data, a better way to do this analysis. So soon we'll be updating these plots, probably by next week. But you can see that in case of Curiosity, you have such a good agreement with data. In case of Perseverance, yes, you have good agreement. However, during night time at coldest temperatures, EMIRS values are systematically lower than what is measured by Perseverance. Now another thing is, comparison between orbiter and rover is that rover measures a very localized observation. And so these things depend on what type of surface it is measuring. So thermal inertia. And so thermal inertia can vary significantly. So in 1 week, it is in a place where temperatures might be lower. In other weeks, it can produce higher temperatures just because of changes in thermal inertia. And so the idea is to take an average so that the rover also covers a bunch of thermal inertias which you can average, and same thing with the orbiter. And so if you take the average for 30 sols or for a period of a month, so on the left you can see on the vertical axis you have the temperature in Kelvin, and the horizontal axis is the local time. And you can see the dawn and dusk by these two vertical lines. The black line is prediction from MCD, Mars Climate Database. Curiosity data is in green, and HOPE is in red. And on the right side, you have the temperature comparison, same thing. MCD is in black, then you have Perseverance, and EMIRS is in red. And overall, you can see there's a good match, but there are instrument to instrument systematics, which we want to investigate much further. All right. So let me show you some other type of data that you get from EMIRS. So this is a short video which will show water ice optical depth as a function of local time. So this is a full map of Mars, and on the vertical axis you can see the color coding, water ice optical depth. Blue is more, white is less. Yeah, so as you can see, the beautiful thing is that you can capture in real time, hour to hour variability and these things such as water ice, optical depth, which was not possible earlier. Then I'm going to show you a sample of dust, which you can see with EMIRS. Yeah, you can really see how it is. It starts at one point and then it spreads throughout the planet and so on. So this is great. This is a great tool to study the climate of Mars, the weather of Mars, even atmospheric escape depends greatly on dust. So this is an excellent data set for all these problems. All right. Then finally, I'm going to talk about the EXI imager, which sends these stunning images of the full disk of Mars. So as I mentioned earlier, the probe reached orbit on February 9th, and on February 10th, it observed this disk image on the left. You can see, the Tharsis region in all its glory. And this is the beauty of this instrument, that you can see the full disk at a time. This is another image. You can see North Pole, and I can just go on and on looking at these images. This is just stunning. You can use it for public outreach, plus there is a lot of science data in it. For example, studying clouds and ice and so on. You can also see Phobos and Deimos in these. So that is also very interesting. This is another image from EXI. This is the famous Valles Marineris in all its glory. So because we were seeing all these images, and so we thought that we should actually make a photographic atlas of Mars based on all these images. And so we did that. So our Atlas of Mars is now available online. You can go to this marsatlas.org website. You can see all the images. You can download the whole atlas as a PDF. So it's a great tool for students to learn about Mars. And because it gives you the full disk of Mars, and the idea is to track how Mars changes throughout the year. So one Martian year is roughly 2 Earth years. So we will continually update this atlas to show how Mars looks like during, say, northern summer versus, during dust season and so on. So we want to capture all of those things, which will be available here. So we combined, so EXI, because it sends so many stunning images, we developed a way to combine all these images to create a full map of Mars. And so this image that you see is combining more than 600 photographs. And you can see that in the north you don't have much coverage, in the south is completely blacked and we have cropped it out. But you can see this is directly from photographs. And this is one of the figures that we made for the atlas. We also have an interactive version now, which we are working on. And we will load it with different layers of data so that you can click and you can obtain surface temperature or atmospheric temperature or other observables just using this kind of interface. On the left, you see this butterfly-like feature known as like a sulci, which is right besides the Olympus Mons. On the right, you see an image of clouds. So you can do a lot of things if you're interested in studying the Martian climate and weather. So this is a great tool for that. Then let me go with the eMuse instrument. So one of the most interesting things that we observed so far is auroras. Now, auroras have been observed on Mars. People have observed diffuse auroras, discrete auroras. even daytime auroras called proton auroras, which were first discovered with Maven. So in this is from EMU's observation. This is the oxygen 130.4 nanometer line, and so on the right you see sunlight and all. In the background you can see these dots, which is UV coming from stars. But during the night side, you see this emissions going for hundreds and hundreds of kilometers, and these are very long. We are very extended auroras, which we see a lot with Hope, which we haven't seen before. So we see these discrete auroras in about half of all observations, and so we have a lot of data. So these are long, worm-like discrete auroras, which you haven't seen with other missions, and so this is very interesting. The other thing that you see in addition to these worm-like discrete auroras is much smaller, patchy discrete auroras. And then there are auroras you see which are associated with the crustal fields on Mars. So as you know, Mars once had a global magnetic field and it got lost, but it still retains magnetic field in the crust in some bits and pieces. And so you see auroras because charged particles are trapped there. So we do observe them, and we are working on a manuscript, and you'll see a result soon. And with that, thank you so much for the invitation, and I would have loved to come in person, but maybe next time. So thank you so much.
So, any questions for our speaker? I know you are willing. No. Okay, you have a second question.
Dimitra, I like very much your talk, but I have a humoristic question. Is for you more difficult to get the visa to come to Spain or to prepare a paper on Mars?
I think Spanish visa is much more difficult. So with Spain, I don't know. So I never had any issues with coming to Europe. I travel there quite frequently. But let me tell you a story that back in 2020, I was invited to give a talk at Canary Islands in Spain. It was European Astrobiology Institute had a conference, and so I had done my visa and everything, and ticket was booked, and I was about to come, and then, as you know, the pandemic started, so the conference was cancelled. So I could not come to Spain, and now this. So let's hope, third time is the charm.
So let's hope that the visa is not going to be so difficult for planet Mars. Okay, Dimitra, so thank you so much. We expect to have you potentially as soon as possible. You are, of course, invited to visit us at Madrid.
Yeah, looking forward to it.
Okay. So, the session is going to end right now with a coffee break, and after this small coffee break, we have the book presentation. So thank you very much for your attendance. very fast. But actually, it's the presentation of this book. We produced this book during the COVID lockdown, so we felt like we were actually traveling to Mars because of the isolation. So I will pass the... No, de pie. ¿Puedes?
Okay. Good afternoon. Actually, as José Luis indicated, that this book was finished last year during the pandemic time and was not presented because to present a book in 2 dimensions, I didn't like it. So we left this simple ceremony among friends that of this book. And unfortunately, the editor is sick with the new version of coronavirus. I mean, as you know, this infection is so volatile, so flexible, it's transforming every day. Actually, 2 persons that would like to be here, they are not able because, I mean, even it is not dangerous, but it's not good. Okay, so the idea of this book was as prepared during the pandemic, everybody was locked down. And so we used, but fortunately, we were very lucky that the electromagnetic waves were not attacked by the virus. So it was at least a good thing. So we decided to put together, and really in this book is recollecting the beginning of our group in Complutense. Actually, to my idea from the beginning was not to participate spontaneously in one mission, but to create an environment. And the environment means that we had 15 PhDs already in this contest. Some of the PhDs was a speaker today from United States, Germán. He made the thesis in our group with Professor Paco Valero. And this is, I mean, and still our activities are running. Now, some people that originally came from Complutense is in the Polytechnica, like Salvador, but anyway, is this idea creating, and we reflect here that we start from, I will not say 0 level, but -5, maybe, because it was not a space, a culture in the Complutense, as I said this morning, and to try to involve it, there is different groups. The group of the Pilar about, they were able to compute the eclipses of Phobos observed by curiosity with a precision of 1 second. So it was a lot of this action in fluid dynamics, let's say the atmospheric issues, radiation issues. So and they are the people. The nice thing of the group is, fortunately, that we are in different departments and we are in different faculties. Even we are in the same university. In this way, paradoxically, it looks that because the idea of the people is to say, to have a building, this is the institute. No, we don't have, and in this way, we are more free. Because I will say in anecdotic that my coordinators are, I'm full professor in applied mathematics, but in computer science is other faculty. But my department, because as you know, at least in Complutense, the professor, we have 2 coordinates. X is the department and Y is the faculty. So you can move in a 2-dimensional plane, and so I know, when the people try to localize me in the X dimension, I am in the Y, and when they try to localize me in the Y, I am in the X. So in this way, it's a positive aspect of these things. Okay, anyway, the reason of the project is that the participation in missions and projects. We were able to establish, as I indicated this morning, particularly with Finland, I thank you very much, Professor Ari-Matti. We start to meet and to interact in the Beagle 2 mission, actually in Open University, and we remember, but we continue this collaboration because what I found at the time, that even our knowledge and contact were zero. In the group of Professor Ari-Matti was the university and the industry. So it was a good, I learned how to combine the two actions. After that, through Professor Ari-Matti, we start to collaborate with Russia, with IKI, and the rest, it was the famous project MedNet, that allows to create an environment of research and motivation and projects and know-how and how-know that is appearing. Now is applying as it was indicated. And the manifestation of this friendship is not only the question of physics, engineering, is that today Professor Oleg Korablev was able to talk. As you know, the situation is very critical, was very difficult, not only technically, but also in many issues. So, but it's a manifestation that the last month I was able to give, they invited me to give a closing lecture in Russia about studies which are shared by several universities, as you know, but the problem now is the participation of other countries. As you know, a war has many unfair. So I gave a talk. I was very happy with many people. And as in Italian say, I like this letter, we have to go in parallel convergence with the people in politics and in industry, but in parallel convergence. As you know, the mathematicians say that the straight parallels, they meet in infinity. And the railway workers, they say they met in the railway station. So really is a way of this. So reflecting that, the whole set of actions we have internationally, nationally, and so are reflected in this book. It's not, actually, to some of you, I already sent a book, but you will have a copy of the book. Actually, today we have 5, but tomorrow we are going to have another 10, because the question is that the editor, it was not able to come, and so it's thing. But anyway, I will be very happy to give, and if there is not enough, in this way you are obligated to learn Spanish, okay? Okay, to tell. So I thank you very much for coming to this meeting that in a certain way for us is like in the movie Start Again, because I hope that the next academic year, also in the faculty, we will start again, because until this year I gave my classes by a teleconference, so in 2 dimensions. Still, the NASA or ESA don't have access to the 3-dimensional conference. I hope that in the next future we will have the video conference. Actually, I will say, I saw an implementation of the 3D teleconference in the Italian television in the Festival de San Remo. In Festival de San Remo, they show there, and it was a good test to verify that they were not real. But anyway, it was in the Italian. So actually, we are, I think, even the complexity of this period, we are in a very good period. In my idea, new scenarios are appearing, are creating new ideas, and I hope we will arrive to some asymptotic quiet place, conceptually very soon. So it's only to tell that, and really this book, as you can see, are many authors, all the people from the group that are involved in the research we were done. The authors, editors, we appear at 3 because by the logistic of the editorial, we must say, and is Mapi is to Maria Pilar is not able to come. Maybe she will come this week. A good news that she was become mother recently, so it's a good and the other author is Professor Jose Luis. You have to come to say some words. After there in the room, Professor Salvador Jimenez, that fortunately for me is that even he was my first PhD student, still we are friends. So there is long time that we collaborated in RENS with the retrieval analysis of the UV sensors. Actually, in the RENS, our contribution was really the ground temperature sensor that apply also in geology. And why that? Is because a mathematical issue is that to evaluate the first derivative and the second derivative of the temperature in function of the altitude, you need 3 points. For the first derivative 2 and for the third 3. But if you take the measure very close in the rover, they are not good measure because they are polluted by the thermal issues and so on. So we decide to measure with infrared the temperature of the ground, which is a discontinuity and is given. So we already, with Salvador, make the analysis of these instruments, and was a good collaboration. I mean with that. So I pass the word to Professor Salvador, if you like to.
Okay. Well, thank you very much. Is this on or is off? It's just a maraca.
If you want, you can speak with the it's a maraca. You can speak with the mask.
Okay. Well, I don't mind. Yeah. Well, I have not much more to say. We have a saying in Spanish that says, "Donde hay patrón no manda marinero." So, okay, you can translate that through Google. And but I remember when we started in all those ideas, his students were saying among ourselves, but we have never worked on those things. But what is Luis proposing? But then he said, yes, the law of physics are the same here than in the sun or Mars or wherever. So, okay, and mathematics are still the same. So, okay, good. So he gave us a lot of confidence, and then we could second his proposal and work with him, and happily we have made many successful joint projects. So. But nothing more to say. And the book was, I think, there was only a problem, is that we were too many people. So it was difficult to have a common ground and a common problem solved and so. But Jose Luis organized perfectly, and after a few settings, we all could work together with no seamless, as they say. So. That's it. I have nothing more to say. So, Jose Luis, la maraca para ti. Usually they go by pairs, but.
Okay, so thank you. So I guess everything has been said already. So if there are no closing remarks, we can.
No, I like that somebody see the face of the names that appear. Mariano, where is Mariano? I'm here. He was our last incorporation, but not less.
Yeah, thank you. No, Thank you so much. So For those of you who may not know me, I am Mariano Sastre. I am currently a lecturer at Complutense University, and I am very happy to have joined this team. In my case, it is in the group of the atmosphere of Mars. My background is in the atmosphere of the Earth, but as it has been said a couple of times, the physical laws are the same in the Earth and in Mars. So we can transfer our knowledge gained in the Earth to apply it in Mars. So I am happy to be here. I will, let's say, be on behalf of all the meteorology team of this book in Mars, the group of Paco Valero, who has been earlier mentioned, and I think it has been mostly said. So thank you so much. I don't know if José Luis can add anything.
No, I mean, we'll be okay like this.
Okay, no, actually, as you can see in the chapters, every chapter is devoted to a field. I mean, radiation, eclipses, atmosphere. So is to see you can identify. So David Gizero, can you come in, please? He was the first one, he initiated in the group the fractional calculus applications, and he spent some time in the University of Bologna with Professor Turchetti, and he made a good contribution for them. So, and now we are applying to the dust dynamics. Okay.
Yeah, well, what to say? In fact, I came here as an old student from Professor Vázquez, and I make the thesis with him. In principle, I start with solitons and nonlinear waves, and then we came into fractional calculus and local problems, and then we move into Mars and applying everything to different fields of science. And I think this is a very great adventure to be involved in this group. And thank you.
Thank you. To finish, I will say that it's not only a rhetoric, so say that the laws of physics are the same in Mars. I will say, frankly, the personal experience I have in the Spanish ministry, where the structure, bureaucratic structure, are very peculiar. And I remember discussing about the support. They said, but you don't have previous experience with the Mars, with the space. I said, oh, if for you it's okay that I worked a little bit in Maxwell equations and in fluid dynamics, maybe I start to apply. I don't know, the expression they used was very strange, but finally we got it, because I was calling every day, so you are telling me that the laws of physics are not the same in Mars than in the Earth? Okay, so by the exhaustion method we got the first time. Okay, so thank you to you for to be that, and with the books, I will say, some of you, I know you have a copy of the book, but tomorrow we will have, and is...
Yes, we're going to do a raffle of